Yeah, thank you. And I would like to yeah um, uh, to introduce Professor Bedford from Stony Brook. Yeah, he will talk about um, okay Henon. Yeah, complex Henon maps. Yeah, sorry. Okay, yeah.
Well, thank you very much. I am quite pleased to be here to have the opportunity of visiting Italy and seeing so many friends, old and new. And this is promising to be a very good opportunity for me to learn new things. And my plan for this talk is to talk about complex Henon maps, but the course in the progression I'm going to take in my talk, I hope will be accessible to the people who are not specialists in exactly my area, because this, you know, like all good conferences, this represents a lot of different areas of mathematics. So I hope, be clear. And if I'm not, let me know and I'll try to explain myself. So what I want to do is talk about complex Henon mappings. And so I'm going to talk about dynamical systems. And so let me just start at the very beginning. By dynamical systems, I mean we have some mapping from a space to itself. And we're looking at what happens when you apply the mapping to itself some number of times, and then this number goes to infinity. So, you know, it's a question that on the face of it seems extremely hard to say anything at all. So, but it turns out you can say quite a lot of things. So let me define one of the basic objects that people look at in looking at dynamical systems. You can take a point, or it doesn't have to be a point, it could be a set, but the stable set associated with this point x naught is all of the points in the space such that in forward time, the orbit of y chases the orbit of x. So the distance between the two go to 0. And the unstable set, the word unstable is a little bit grammatically wrong. It's actually a stable set in backward time. So for the unstable set, you're actually looking at the backwards iterates, and you're looking at the stable set for the inverse mapping. So I'm talking about now invertible dynamics, which is what I... Oh, let me see. Where? Last line. Oh, as n, so here, the point is we're looking at Fn as n goes to plus infinity, and here we're looking at F minus n as n goes to plus infinity. Yeah. Sorry. Yeah, I meant to say the distance goes to 0 and the n is going to infinity. I should have been less lazy. I should have actually done you the honor of writing out what I had to say. But okay. So what do I mean by Henon maps? Well, these mappings are very closely related to polynomials. They're polynomial mappings. These are mappings that can be written in this special form. In other words, I have a polynomial, x is a complex variable. I have a polynomial of one variable, x, and I subtract the other one, and then I put x back in the second variable. And so a second component. And so this, this has an inverse, which you can easily check. So this is a polynomial automorphism. Now, when I write this down, it looks like an extremely simple mapping. So it looks very, very specialized. But in fact, there's a theorem of Friedland and Milner that says when you're looking at polynomial automorphisms of C2, everything interesting is of this form, or else conjugate to it. So this is actually everything you might ever want to talk about if you're talking about polynomial or automorphisms in dimension 2. So what do? You follow the pathway that people have done for complex dynamics in dimension 1. You're looking at polynomial maps, and you want to be looking at the set of points that do not escape to infinity in forward time, or again, this is the points that do not escape to infinity in backward time. Okay, so we have invertible mapping. So every time we have something forward, we put a plus. For the backwards things, we put a minus. And so the set of points that stay bounded in both forward and backward time, this is K. This is, I mean, it's a theorem, it's a compact set. And then there is the set of points that escape to infinity. We can look at the complement of these things. And one of the theorems is if you do not stay bounded, then in fact you go to infinity. Okay, that's another theorem. So now I'm looking at holomorphic dynamics. These polynomials are holomorphic. And one reason to study these is that you can apply a lot of results from complex analysis. And so you can have other tools that you can use. And so we're going to be looking at something called the Fatou set, which is the open set where the forward iterates form a normal family. So the reason we're talking about normal families, okay, is this is a topic from complex analysis that people studied very well. And being a normal family is equivalent to being equicontinuous, or it's equivalent to being pre-compact. So this is what you would mean, by stable behavior. In other words, when you start looking at the iterates on this region, in fact, are a pre-compact set. So that's what you can hope for in terms of stability. And it's easy to check that the interior of K plus is a set where the iterates will be a normal family because you're staying bounded. It's a old elementary theorem of Montel, or one of the easier theorems of Montel, that this is a normal family. And then over here, if you're escaping to infinity, you're actually escaping to one point at infinity. And so this is also you're a normal family in the complement of K plus. And the complement of the Fatou set, by definition, is the Julia set. So this is where, if there's going to be chaotic behavior, this is where it'll take place. And it's easy to check this is the boundary of K plus. Now, if I want to put in minus signs, then I just take the inverse map and I do the Fatou set for the inverse map and the Julia set for the inverse map. And so I get the backward Fatou set and Julia set. And then if we take the intersection of these two, we get something that could be called the Julia set. I mean, it is very justifiable to call this thing the Julia set. Now, let me, for the people that are more expert, I can look at the quadratic family. In the previous century, the quadratic family was very thoroughly studied. You can look at the parameter space, the Mandelbrot set here, and if you're inside the main cardioid, it's a theorem. If you're in the main cardioid is defined by the property that there is an attracting fixed point. Okay, and so that's this thing here. If you're an attracting fixed point, it will have a basin of attraction. I'm drawing dynamical space here, I'm drawing parameter space up there. In dynamical space, there will be some basin of attraction, and it's a theorem that this is bounded by some Jordan curve. Okay, the Julia set is the boundary of the basin. It's also a theorem that is, if C is not zero, if C is zero, you know the Julia set will be the circle. If it's not zero, it'll have Hausdorff dimension bigger than 1. Okay, that's a theorem, not trivial theorem, but theorem. And so that's what things look like. Now, you can ask, and it was asked and answered, are there any mappings that have special Julia sets? Well, Fatou gave a theorem that says if you have a tangent, so your Julia set usually is a crinkly set, you know, I was saying before it was having Hausdorff dimension bigger than 1. But if it actually has a tangent just at one point, then in fact the mapping is either going to be the z goes to z to some power d, and then your Julia set is a circle, or it could be a Chebyshev polynomial, and then your j would be a interval. Okay, and so you have actually two. If you're going to study things, you might want to start and with these two very special cases and see if you can understand them very well. So it would be natural to say, well, could there be Henon maps for which the Julia set actually is well behaved, some kind of either smooth or analytic or semi-analytic or something kind of set? Well, back in the beginning, Fornes and Sibony and Hubbard and Obersforth considered these quadratic Henon maps. And they said, well, suppose A is very small, C is very small. This is like being in the main cardioid because you have a unique attracting fixed point. Okay. And so we're in this situation here. Now, mappings like this have come up because, I mean, they've come up in the past for people doing complex analysis because early on, it was wondered, well, what kind of uniformization theorems can you have? Could you have some kind of complex C2 space inside of C2 space? You know, in one dimension, if you have something that's equivalent to C and it's inside of C, it has to be all of C. They're asking the same question in dimension 2, and going back to Fatou and Bieberbach, they know that if you have an attracting fixed point, its basin of attraction. Anyway, Fornes, Sibony, and Hubbard and Obersforth, I mean, what I've said so far was just a lot of talk, recalling a little history. In this particular case, what they did was they analyzed the boundary of the basin of attraction, and they said the Julia set, well, it's not hard to see that the Julia set is the boundary of the basin, but what they said was that the boundary of the basin is a topological 3-manifold. It's fibered by complex manifolds. Okay, so you're fibering this thing by complex manifolds, and it's a topological manifold with boundary. So the boundary is nicely attached. And in fact, the J plus is a union of stable manifolds. Okay, so that's nice. And so it seems like things are looking good. If we just find the right values for A and C, we should be able to get the one that smoothens out. You know, as happened in dimension 1, you move around in the main cardioid, and as soon as you hit 0, in fact, your Jordan curve smoothened out and became the circle. But in fact, if you're looking for any special mappings for in the complex Henon family, for instance, comparing with the one-dimensional case where you could either have the circle or the interval, if you have F being any composition of Henon maps, then the forward Julia set is never C1 smooth, even is never a C1 manifold with boundary. And it's also not semi-analytic. Like you could think of this as being a C1 manifold with, I mean, of course, it's better than C1, but it's manifold with boundary. But J plus is not even smooth as a manifold with boundary. And also, it's not even semi-analytic. So in some cases could imagine that you could have something defined by real polynomial equations or inequalities, but that's never going to happen. So, but what I should say is that the point of these theorems, yes. What I mean here by semi-analytic, I mean even locally semi-analytic. That's what I mean. And here, these are, I'm intending them to be local conditions, even though I maybe, yeah. Right. All right. So I'm going to mention a bunch of theorems, and I do have a web page, and every paper that I ever mention, I taught a couple of courses on complex Henon maps, and a lot of the papers you might want to look at, they're on my web page. Until somebody tells me I have to take down my web page. And so let me just go back historically here. My own connection with complex Henon maps goes back to 1987, when I happened to be in Paris visiting Nassim Sibani, and Hubbard was coming along. He was going around and telling everybody, I've got these great things. Okay, Hubbard and Duadi had had a great success in analyzing the one-dimensional maps, the quadratic family, z squared plus c. And Hubbard was very full of excitement and enthusiasm. He thought, well, you know, just add another variable. You've got two-dimensional mappings, and heck, you know, I'll do the same thing, you know, no problem. And so he proposed that this was really exciting stuff to do, and he got me interested in it. He got Sibani interested in it, a lot of people interested in it. And so what did he do? Well, in one dimension, you can define a green function of the filled Julia set, and you can do it by taking your map, iterating it n times, taking logarithm, you take log plus, so you're taking the maximum with 0, so you don't have any minus infinities to think about. And so you divide by the right normalization, because the degree of this guy will be 2 to the n. So when you're taking logarithm, if you want to have some convergence, you need to normalize it by the degree. And when you're looking at this map, you can see when you're applying it and things are getting large, the x coordinate is going to be bigger than the y coordinate, and the x coordinate is going to look like the square of the y coordinate. So when you're taking logarithm, instead of taking the modulus of the whole thing, you could just take the x coordinate, and that'll do the trick. When you do this, when x is non-zero, you're having a harmonic function, and in more than one variable, this is a pluriharmonic function. So it's a fantastic thing. I mean, you know, people like me, my heart, you know, starts beating fast when I see something's pluriharmonic, you know. Wow, you know. And so anyway, this is the green function. And so this is something that's pluriharmonic on U plus. Hubbard looked at this thing, and Hubbard said, well, I've got this set. It has this beautiful pluriharmonic exhaustion. There's also the set K plus, which is where this thing is 0. But he thought, well, what we should do is analyze this great escape set and see what happens. So he wanted to analyze U plus. And I said, G plus out there is pluriharmonic. That means it has a harmonic conjugate. So it has locally a harmonic conjugate. So you add on your local conjugate, and you have a holomorphic function. So you can look at its level sets. Those will be that will give you a holomorphic foliation. So you've got this holomorphic foliation on U plus. And furthermore, Hubbard observed that if you take e to the G plus its harmonic conjugate, well, this isn't the way he defined it, but it's the way I define it. I mean, he had his own fine way of defining it, but this gives you something that's the Butcher coordinate, and that means that this is a coordinate that semi-conjugates you just to x squared. Okay. Now, this has I said you have a local harmonic conjugate Well, if you're inside of this region, you can see that there's exactly one non-trivial element of the fundamental group. And when you go around that, when you go around that element of the fundamental group, you come out by 2 pi. So when you exponentiate, you get a single valued analytic function. So in fact, this function phi is well defined on the set V plus. Okay. Well, it's easy to see that when you take V plus and map it forward, it maps around, goes around twice, maps inside itself. So when you come backwards, you get bigger. The whole escape region is the union of these pre-images of V plus. And it's not hard to see that the function phi plus that I just defined back here, okay, this phi plus defined in V plus, in fact, if you iterate, if you take the pre-image of V plus, that's an h to the -1, phi plus does not extend, but it does extend as a multiple value function along any path. And the topology here is not finitely generated as an additive group. So you've got infinitely generated topology. Something interesting, okay? I mean, Hubbard was quite right. This is interesting. And you have you can think of this covering space anyway, you can think of this as a covering space, which is the Riemann surface you would get by taking the function phi plus and analytically continuing it as far as possible. So one of the questions that Hubbard was raising in those days, well, let me see, I should say here, did I say it? I don't think I said it, but I should have said that this set U plus is independent of the map. It depends only on the degree of the map. So all the mappings of the same degree have homeomorphic U pluses. But you can ask, what about the biholomorphism type of U plus? Okay, does that change when you change F? And so the way they approached this was to look at the covering space and ask, well, what are the covering transformations? And the covering transformations were looked at by several people. And finally, very recently, an answer to this question is that the biholomorphism type of U does exactly determine F. And specifically, if you have two Henon maps, Rat and Nepal showed that if their escape regions are biholomorphically equivalent, then they're equal in this sense, okay? I said equal, but the point is you could have some d-1 roots of unity, beta and gamma, and then you can have a d plus root of some beta. So this is some number of, less than d cubed transformations. So you take this linear map B, okay, just plain diagonal linear map B composed with F1, B, and L, and that'll give you F2. And that's the only non-uniqueness you can have, okay, except for this very straightforward non-uniqueness. These guys are, I think this is a really beautiful answer to Hubbard's question. So also in Hubbard's time, you've got a foliation on this escape region. Hubbard described the foliation, and but you've got a foliation on U plus, you've got a foliation on U minus, and they interact and they overlap in a big set. And so you can look at where this wedged with that gives you 0. So that's exactly the place where these foliations have a tangential intersection. And Hubbard says, that should be critical points. And I agree with him. Those are critical points. In fact, we agreed with him so much that Smiley and I sat down and worked on it. And it turns out that in the Henon case, the critical locus is always non-empty, okay? So you'll say, well, if I'm studying dynamics, perhaps the escape region is not the place I'm always looking at, those are the points that are transient and forward and backward time both. They're also the, okay, here we go. There's also the set of points where you're in J plus or in J minus. Okay, so these are sort of in the boundary of this double escape locus. You can also define what the critical points are in that case, and you can actually prove some theorems about it. It's still a question in general, what is this? So it's always a non-empty Riemann surface. And people have described this Riemann surface in a couple of cases, but otherwise it's pretty much an open question. What's its nature? And so I would say there's a problem. How would you describe critical points in general? So you have complex Henon mappings. There are a couple of regions associated with that where you know exactly what the critical points are and should be. But then for the rest, it's a point. Of course, in some cases, like in dimension 1, a critical point is where the mapping is locally branched. Okay, that means where the mapping degree locally is bigger than 1. Here we're looking at invertible maps, so the mapping degree does not tell you anything about critical points, but these are other behaviors that are critical points. And so, all right, so this is, we're going to say goodbye to Hubbard now. Let me go back. See, Hubbard wanted to look at the place where the green function was positive and pluriharmonic. There are also people like me who like potential theory. So what about potential theory here? If you have a compact set, the green function is some function that's continuous globally. I'm now in 1 dimension. I mean, life is infinitely simpler in 1 dimension, I would say. It's going to be globally continuous. It'll be 0 everywhere on K. And as you leave K, it's harmonic. Okay. And it's harmonic looking like log Z plus a constant as you get out near infinity. Okay. So when you're in this situation, you can think of this green function as representing electrical potential or voltage. And when you apply the Laplacian, that gives you the charge distribution that's induced on the boundary. So you can think of this as being inside the Riemann sphere. So I've compactified C to the Riemann sphere. At infinity, I put a negative unit charge, and I look at how everything distributes itself. That induces a charge. If K is a conductor, that induces a charge on K. And so that charge is the Laplacian here. Now, if I want to go from dimension 1 to dimension 2, and I want to talk about dynamical systems, I need something that's invariant. Now, the Laplacian in complex dimension 1 is a conformal invariant, but it's not actually an invariant. It's a conformal invariant. And so we need something in Cn. Now, in complex dimension 2, the Laplacian is not a conformal invariant. It's a nothing. It's just a, it's something we just let the PDE people do. And so, but we can look at this round D, and you can see that you're taking a derivative with respect to Zj, and then you're throwing in a differential here. And that thing is a holomorphic invariant. And if I add D and D bar, I get straight D, and then DC is the imaginary part of round D. And to get DDC, if I take 2I DD bar, that looks like this, and these are all holomorphic invariants. Okay, and so you can think, well, we could try to do some potential theory. So for some length of time, people have talked about some kind of analog of the green function in higher dimension. And if you want to have some holomorphic invariants, you need to work with something pluri. So I mean, I'm calling it pluri complex. You look at plurisubharmonic functions that are having the right rate of growth, you make them less than or equal to 0 on k, and then take the supremum. And then for technical reasons that we don't have to worry about, if it's not actually continuous, you make it upper semi-continuous, so it'll be plurisubharmonic, or be subharmonic at least. So, so you can look at this and you can apply the complex DDC, which is the invariant version of the Laplacian, and you can square that thing, and that gives you a measure. And this is what, with Al Taylor, we're proposing as the pluri-analog of the equilibrium charge distribution, and that we call that the equilibrium measure. And you can say a number of things about this. You can write a paper about it even. And so the support, among other things, is an interesting property. We call it the domination principle. The support of this measure, in fact, is the Sheloff boundary of K. So the Sheloff boundary is an interesting boundary for complex analysts. It's the smallest closed set that lets you have a maximum principle. So you know that the maximum principle says that when you're taking the maximum of a polynomial, the modulus of a polynomial over some compact set K, the maximum is attained at the boundary. Well, Sheloff boundary was the minimal boundary that this will work, the minimal closed boundary. Okay, so that's an interesting property. Okay, and looking forward, in the dimension 1, when you're doing complex dynamics, you have the Phil-Julia set. The Julia set is the boundary of K. Okay, and so, in fact, for complex Henon maps, you'd like to instead take the Sheloff boundary. The whole boundary is just too big, too many points, too many irrelevant points. So I told you that my introduction was when I was visiting Sibony in Paris, and we started talking about it. Well, we were thinking when you're looking at one-dimensional complex dynamics, most of the theory, you know, that was done by Fatou and Julia was done using Montel's theorem, very, very powerful theorem on normal families. And then later, with Sullivan's theorem, you know, they started using quasi-conformal maps, and these things just aren't available in dimension 2. They're just, I don't know what to say. Whoops! Oh, I moved myself ahead. Okay, so here is anyway, with Sibony, we were thinking, well, what you want to do is be looking at your green function. You're interested in what gives it character. I mean, you can think of where a function is pluriharmonic. Well, in other words, where it's pluriharmonic, it's, you know, too nice. You know, it's just too nice, you know. And when you're getting down to where it's inducing charge, that's telling you about what its character is. Okay, so you're looking at the, so to speak, the charge, okay, induced by this guy. So you've got mu plus and you've got mu minus, and you take d bar of both of them. And you can interpret it as a current. So this is like a distribution. Distributions are the dual space of the test functions, and instead you can try test forms. And they have obvious invariance. You take mu plus, you pull it back, and multiplies by d. You'd have mu minus, you pull it back, and it divides by d. And it's easy to see that if you take the support of mu plus and minus, you're going to have exactly j plus, because if you have some open set, this little orange ring is an open set here. If it intersects j plus, it has to intersect the support of mu plus, because if it doesn't, that means that mu plus is 0 inside this orange ring, and it has to be everywhere harmonic. But then, since it comes down to 0 somewhere in the interior, that contradicts the minimum principle. Okay. So And we talked about this, Sibani and I, and it's very strange. So when you're looking at the set K, that's the intersection of K plus and K minus, the G plus is like a green function for K plus, G minus is like a green function for K minus. It's totally, from the point of view of a complex analyst, it's totally bizarre that your green function should be pluriharmonic someplace. That's totally bizarre. But in this case, you just check it, and the maximum of G plus and G minus is the pluricomplex green function. And when you take this guy and square it, it's actually mu plus wedge mu minus. I mean, this is a nonlinear operation and things, but that's the way things work. So very curious. And so what this tells us is, we already mentioned this as being a Julia set. It would also make sense that the support of this measure should be, that's the Sheloff boundary, should be a Julia set. And it's easy to see that J star is inside of J, but it's a question that basically from day one we were asking and scratching our heads, and we're still scratching our heads. We do not know if they are always the same or not. Okay. For instance, Smiley and I have written some papers, and paper number 3, in the paper, among other things, it says if your set K is totally disconnected, which is a case. I mean, there are a lot of interesting dynamical systems with K totally disconnected. In that case, then these are all the same. But another example is, I'm not going to say too much about well, maybe. So what does it mean to be hyperbolic? Okay. Well, if you want your mapping, if you want your Henon map to be hyperbolic, the right definition is you want it to be hyperbolic on the set J. I mean, you can't require that it's hyperbolic too many places because that won't be reasonable. But the set J, you want it to be hyperbolic on the set J. That means on J, you have a splitting of the tangent space into some subspace called the stable and unstable directions. And on the stable directions, your mapping is uniformly contracting. On the unstable directions, it's uniformly expanding. And not too long ago, Dujardin proved that this is a theorem that I would propose is more non-trivial than it looks. So if you require that your mapping is just hyperbolic on J star, then automatically you can conclude that it's hyperbolic on J, and J is equal to J star. So it sounds like he's tightening up the definition of hyperbolic somehow, but in fact, this is pretty, it's a more non-trivial theorem than you may think. So this is the obvious inclusion. I mean, this is, in other words, this is some kind of boundary, and whatever the boundary is going to be, it has to be in the boundary of K plus and boundary of K minus. So this, if you think about it for 1 minute, you know, then this is the obvious inclusion. Okay, but are they going to be the same? Okay. So why am I getting stressed out about J minus? I mean, it sounds like Hubbard originally made the definition of J that looks so nice you wouldn't blink. You know, you'd say, hey, that's, yeah, it's J. J plus intersect J minus, that's J. Well, the thing is, J star comes in a lot of ways. And for instance, if you have a couple of saddle points, okay, you have a stable manifold and you have an unstable manifold, and you look at all the points of intersection, okay? Look at all the points of intersection, take their closure, and that's J star. Or suppose you take all the periodic points of saddle type, okay, take their closure, that's J star, okay? So it'd be very nice to know, is J star smaller than J? Is it equal to J, okay? And also in terms of measures, if you take the saddle points of period n, divide by d to the n, then that converges to mu, the invariant measure, okay? And so that tells us, among other things, that if you look at all your periodic points, you know by algebra that there are d to the, periodic points of period n counted with multiplicity. Just by algebra, you know that there are exactly d to the n of them. And this tells us that if it's saddle type, then it automatically has multiplicity 1. And this tells us that the periodic points are asymptotically saddled. So when you're taking, without knowing anything about your map, you can know that when you take a lot of periodic points, most of them have to be saddles. Okay, so let me get back to the green function. Okay, so remember I was drawing this picture here. When you're taking in the one-dimensional case, you have this picture. Well, here is a cartoon of K plus and J plus, the boundary. We're saying here L, let L be any complex line, okay? Let it be any complex line. Now, when you have a current, you can slice your current on a line. And this says that when you slice the current on the line, when you slice G plus on the line, you get the green function of that intersection. And when you slice the current on that line, for that sliced green function, you get the induced distribution. So your mu plus is something that carries a lot of sort of redundant geometry, but a lot of information. It's a very, very interesting object. Okay. Okay, so now I said it's a current. Suppose I have a saddle point and I look at its stable manifold. Its stable manifold is a complex manifold, and this D super S, that's a disk containing P inside of this complex manifold. I want to say that we have a current of integration over that disk, okay? So to have a current of integration, I need an orientation. Well, something complex has a canonical orientation. I just take some direction V, multiply it by I, take V wedged IV, that's an orientation 2 vector, okay? I'm oriented. And if I apply this guy, I can apply it to any 2 form just by integration, and that is that I'm just going to take this 2 form, integrate it over D. D, has got finite area in this picture, finite area, so it's not a problem that this will converge. And now, when we're looking at currents converging, well, what that means is anytime I put a test vector there, test 2 form there, I put it against these currents, that converges for all phi. So that's the sense of convergence. So treating things as a current gives us a completely new sense of convergence, which is different, like from convergence in the Hausdorff metric or something. This is just something totally new. This was invented back when people were looking at minimal surfaces. And so if you have some funny thing that's almost a disk, if you're trying to find the surface with some given circle as minimal as boundary, and you're trying to find the minimal surface, which is a disk spanned by this curve. If you look at something converging to this disk, well, you could have something that's almost to a disk, but some little spike coming up and moving all around, But if the spike has very tiny area, that thing converges to the disk in the sense of convergent of currents. So that's something we make a lot of use of. And I should say that I didn't say it here, but this is a canonical orientation. And this, with this orientation, we get a positive current. So it's very, very convenient. So, so a piece of sort of philosophy, mu plus is what you have when you take the stable manifold and you make it global. We can think of it as the global stable manifold. So, you know, you take a saddle point, take a little disk in there, and to say that it's the global stable manifold means that if I take this disk and I start pumping it backwards, I pump it backwards n times, I have to divide by the right normalization. I'm sort of making the degree grow by n every time. And the theorem says that if I take this guy and I start pulling it back, filling out the stable manifold, as a current, this guy is going to converge to mu plus. Okay, so this tells me a lot of things. In particular, it tells me that the closure of any stable manifold is going to be exactly J plus. And it also tells me, see, I know that when I pull this guy back, I know that every point of J plus has to be in the support of mu plus. Okay. Is that possible? Well, I'm taking this guy, and after n backward iterations, I need to be able to be saying that I'm putting mass at the point Q. And so I've got to have basically d to the n little disks, fixed, of good size, stacking up there, because I'm always normalizing my d to the n. And so this tells me not only is the closure J plus, but as I get like to some point Q, after n pullings back, I've got d to the n disks right there. So I mean, it's not just in the closure, it's way in the closure. So here's another picture of that. Okay. Now I think I'm sort of running out of time, so I'm just not going to discuss this anymore. But here what I'm saying is that if I take any point here, if I take any saddle point and any saddle point, after n pre-images, I'm going to have a lot of green guys and a lot of red guys there, enough to put mass there. Okay, and so if you're thinking about Fatou-Bieberbach domains, the same kind of argument that gives us this convergence of stable disks also tells me that if I'm at an attracting fixed point, okay, so WS now is an open set, it'll be a Fatou-Bieberbach domain, and if I take its boundary, I'm going to get J plus. Okay, so it's known that you can have Henon maps with infinitely many sinks. So, you could have infinitely many sink orbits, attracting periodic points. And so that automatically that their basins have to be pairwise disjoint. But this theorem says that they all have to have the same boundary, which is J plus. So it's sort of cool. Okay, it's not beautifully laid out. It's all. And one other characterization of this measure mu. Okay, I could take a complex line L1 and push it forward, and then with the right normalization, this converges to mu plus. I could take a line, pull it backward, and as a current, it converges to mu plus. I don't know if I said the right minuses and plus, but anyway, one of them goes to mu minus, one of them goes to mu plus, and then when we wedge these two things, we get the measure mu. We could also do something else. We could take this line, map it forward, take this other line, map it backwards, and then just look at the points themselves. Now we're wedging these two things raw, so to speak. These are unsmooth currents, very bad currents. But if we sum up the point masses at all these intersection points, that'll converge to mu. Okay, so that's another version of mu. Okay, so I want to say a little bit now that there are a lot of things corresponding, you know, I guess I want to say just what I wrote there. A recurrent theme is that if you have a shape of a dynamical set, that should converge, that should correspond to some dynamical properties. So here are a couple of theorems I like about rigidity. Okay, it says that there's only one current, positive closed current, supported on K plus. Okay, but I think I need to move without saying. And then Dean Sebeny weakened the closed condition to DDC closed. Okay, but one thing that I think has really been missing so far in this theory is that you would like to know, I mean, hyperbolicity is a property that's played a very important role. You'd like to be able to know, do you have a hyperbolic map or not? And you'd also like to know, are there hyperbolic maps? And so far in the theory, it's not known. I mean, like there are 3 or 4 maps known to be hyperbolic. Besides, they're sort of the horseshoes, which are obviously hyperbolic. There are the small perturbations of one-dimensional maps, which are also, some of them are hyperbolic. But more generally, for maps in the middle of parameter space, it's not known what maps there are that are hyperbolic. It's also not known how to check a map for being hyperbolic, which in some sense, if you think about the one-dimensional case, there's this classic theorem that in order to be a uniformly expanding map, if all the critical points are attracted to sinks, you're done. Yes. So I will give some I will try to make it in time. Some condition that will be sufficient to have hyperbolicity. Okay. And so what I want to do is talk about something that I'll call the proper locally bounded area condition. So it says there's some large number A and some small number R, such that for every saddle point, I want to look at its unstable manifold and look at it intersected with the ball of radius R. And I take the component containing P. I'm going to have a picture on the next slide. So it needs to be closed in the ball. Okay. In other words, it means it has to go, that component has to go all the way out to the boundary of the ball. And the next thing is that its area has a fixed bound. Okay, those are the two conditions I need. The first one is proper bounded area. Okay, and I will say this is quasi-expanding. If this geometric condition on all the unstable manifolds, if this geometric condition holds, then our map is quasi-expanding. Okay, you may ask, why do I say expanding? But there are a lot of equivalent conditions, and there is a metric that's expanded. Yes. You're telling me what my next slide is going to be. Right. I'm taking your advice in advance. Yes, exactly. So if it's both expanding and for if H and H inverse are both expanding, quasi-expanding, then it's quasi-hyperbolic. And so what Jeff said, okay, is locally proper and bounded area is equivalent to locally bounded folding, or bounded local folding, sorry. Okay, in other words, here I've drawn my neighborhood, my ball of radius R, I've drawn it as a box, which is just fine. And I've taken various possibilities for points, okay? So here is, you know, I have some unstable manifold going across, and I could cut it like this and have something of degree 1, okay? Now, when you have a complex manifold with a proper projection, the degree and the area are equivalent. Okay, so this is where my area is bounded by 1. Here, the local degree under the projection is 2. So the area would be 2 approximately. And here it's something or other. I don't know how to draw something with higher projection, but anyway, the point is that whatever this number is, like 5, that would mean area is 5. So I'm saying that the amount of local folding is bounded. So I'm saying that the local folding is well defined in the sense that this has to go all the way out to the boundary. It can't just sort of stop and, it can't come halfway across and then stop. It has to go all the way up to the boundary, so I have a proper projection. Anyway, these are different pictures of possibilities for this thing. And if your mapping is actually hyperbolic, your stable manifolds and your unstable manifolds make a lamination, which is like a foliation of a compact set. And lamination is equivalent to your local folding just being 1, which is not folding. Okay, so we don't have a dominated splitting. This is a different kind of criterion. Different kind of criterion, because we're going to actually have tangencies. So in this one here, if you do have this bound, a theorem is that through every point of J star, remember the stable and unstable manifolds, all their intersection points are dense inside of J star. For every point, but then if you have a bound, you can pass to the closure, and for every point of J star, you're going to have some guy that is acting like a stable manifold, some guy that's acting like an unstable manifold. And so we're actually going to get these smooth manifolds. We get smooth manifolds. And so we call them stable and unstable manifold. Okay. We don't know whether they're exactly, I didn't write it here. So this guy is a subset of that. So we don't know. This is actually the stable set, and this is this manifold that I'm calling a stable manifold. So I want to call these guys stable manifolds. I know this guy is a manifold. I know this guy is stable. And so this is a subset of that. If I had my iPad working, I could correct this on the spot, but I hope you can. So anyway, so we've got these stable manifolds, unstable manifolds going through all points of J star. And so the theorem here is that suppose we know already that we're in the quasi-hyperbolic world. So our stable manifolds have bounded local folding. The unstable manifolds have bounded local folding. We know we have stable and unstable guys. The only obstruction to hyperbolicity is tangencies. So if there is no tangency, then it's got to be a hyperbolic set. And Dujardin's theorem says, in fact, it's uniformly hyperbolic. Okay, so we're very happy about that. Okay, let me say one other thing, and I will stop here. Well, actually, I have 1 second more. What is an example of mappings that are quasi-hyperbolic? The reason this came up was that Smiley and I were interested in looking at horseshoe locus. Okay, we're interested in how can horseshoes degenerate. So we're looking at real horseshoes, and so it's a theorem that the real horseshoes you can have a horseshoe of degree D. A real horseshoe, its entropy is log D. And so if you look at anything in the closure of horseshoe locus, so this will be after a horseshoe is just stopped being hyperbolic, since the hyperbolic locus is open, if you go to the closure, you're not hyperbolic, so you're something else. Well, the theorem is you've got to be quasi-hyperbolic. And so so partly the theorem is when we're talking about horseshoes, we're not in the hyperbolic case, so we know that there has to be a tangency. So in other words, if you have something that's a degeneration of a horseshoe, it automatically has to have a tangency. What's that? Well, the thing is, our theorem, let me see. I didn't think about that question, and I need to finish in 1 minute. So let me just finish without thinking. So I should say this is joint with Lorenzo Guerini. And so with Lorenzo, also we have some other version of this. If you have a complex Henon map and you know that J plus in fact is just geometrically laminated, okay, in a neighborhood of J plus, or if J minus is laminated in a neighborhood of J plus, then we know that our mapping is hyperbolic. So this gives you, I mean, this is not a checkable condition, but this is a condition that tells you that if you had some geometric vision of what your mapping looked like, if you see something laminated, you can say, yeah, that's laminated. And so you could conclude that it's hyperbolic. Anyway, thank you for listening. Okay.
Hi, so yeah, thank you, Eric, for a very interesting talk. So any questions? If you are on Zoom, maybe you can raise your hand.
Jeff, you were gonna.
Like the basin of an attracting point?
That's a good question. I would like to know. It's not that I did not think about it. It's more that I couldn't give you a good answer. That would be very interesting. I mean, there is the idea of as you're looking at deformations of mappings, we have the definition, of what is a critical point outside of J plus. Does that mean that as you lose hyperbolicity or something, critical points come into K plus? That would be interesting to know, but I don't know what a critical point inside of K plus is. I mean, you can make that. Oh yeah. In the case of quasi, what do we call them? Semi-parabolic maps with Ueda, so critical points would be if you have a parabolic, semi-parabolic basin, critical points are where the asymptotic curve is tangential to the other foliation. There's it's not in my mind right now, but it's there's the asymptotic curve inside of a semi-parabolic basin, and where the asymptotic curve is tangential to the there's an invariant foliation inside of the semi-parabolic basin, and when you have a tangency, those are the critical points, and you always have tangencies. Yes.
So you told us in the beginning there's no Henon map with smooth.
Yes.
Is there a notion of exceptional Henon map somehow? Are there exceptional Henon maps?
You mean exceptionally nice?
Yeah.
Yeah.
Yeah. Like
I don't know. That was sort of what we were wondering. There should shouldn't there be some possible royalty among the Henon maps, some analog of Z goes to Z to the D or Chebyshev or something, and we don't know. We You know, it would, for instance, if the Julia set were smooth, that would be really nice, but don't know. Yeah, I don't know how to. You can tell us.
Any other questions? Yeah, so maybe I can have one. I can have one question. So, so for real functions, so usually we have more startup points than other kinds of critical points. So,
Right.
do you have similar things for complex dynamics? So, in general, I mean not just for Henon maps, but
oh, you mean, so you mean like perhaps entire automorphisms of C2,
so
something like that?
maybe you could have more, always have more, or maybe most of the times you could have more startup points.
I really don't know. I'm sorry. I really have never given much thought to the entire case. Sorry. Yes. Mhm. Yes. Ah, okay. So the question is, in this theorem by Ratnapal, you're saying that if the escape locus is equivalent to the escape locus, then the two mappings are essentially the same. I think it comes down to an analysis of the covering space. In other words, you look at the uniformization, the lifting to almost the covering space of U plus, and you can look at what the induced covering transformations, and the induced covering transformations can be written in terms of the coefficients of the original map. And so if two things are equivalent, they're going to have the same covering transformations. So you have all these equations that these equations have the same coefficients, you know, the coefficients of these mappings are the same as the coefficients of those mappings. And these coefficients are some sort of polynomial or rational function in the original map. And so, in spirit, you would expect things to work out, but it's not so clear. So actually, I can't give you a very good idea of her proof. I think you're right. So you're saying these covering transformations for the covering space are like something or other local development of the Butcher function at infinity. I think something like that is right, because in the original paper of Hubbard and Obersforth, they were looking at the covering transformation. They were also trying to look, maybe it didn't make it into their paper, but they were also talking about the Butcher coordinate infinity. And I think they're connected. Yeah, I think they're connected. But I'm sorry, I should read more papers more carefully.
Okay, so we have the warm food waiting for us outside. So maybe we can have one more quick question if anyone likes, and then we can go outside and ask more questions. Okay, maybe I have one more question. I mean, most of the work here is for startup points. So do you know anyone who works on like a point more general than startup points, like a point that you could have some zero eigenvalues, kind of like
let me see, zero eigenvalues. We're dealing with
okay,
invertible
yeah,
mappings.
right,
Maybe you mean one.
One.
Well, there is a paper that I like very much written on semi-parabolic points, semi-parabolic bifurcation, that was a paper with Ueda.
Okay.
So that there is, and then people talk about, not in the Henon case so much, but for general polynomial mappings that are not invertible, there's a whole lot of interesting work on parabolic fixed points. So these are fixed points that are tangent to the identity, say.
Yeah. Okay.
So those are very, very interesting. That's the most unstable case, and the perturbations are, who knows what. So, but
Yeah. Okay. Yeah. Thanks, speaker again.
Thank you. Thank you for the invitation to come here. I'm very, very pleased to participate. So what I want to talk about today is kind of a step in an ongoing story. And I will, in order to tell you about the step, I need to also tell a certain amount of the story. So I have lots of things to say, but I've given this talk once or twice before, and at least I found a shorter title for it now. So that's a start. I should say, I'm going to talk on the Blackboard, but I'm working off slides I prepared for another talk. And normally I don't find that to be such a great combination, but we'll do our best. If for some reason at the end you're interested in the slides, let me know and I can send those to you. There'll be more precision on the slides than in what I say on the board for sure. So what things do I need to remember to say? So this is joint work and also not yet fully written down. With Roland Roeder, who is at Purdue University, Indianapolis. Okay, so the fact that it's not yet fully written down, you know what that means, right? So no warranty on what I'm saying. I'm pretty confident of most of this stuff, but some of the statements may get tweaked before we're totally done here. So where do I want to start? So first of all, I need to tell you what an equidistribution theorem here is. So here is an equidistribution theorem. Equidistribution in dimension 1, so one variable. So this is by now fairly old theorem due to Lopez-Meunier, accents omitted, and separately Lyubich, okay? And it goes as follows. Suppose you've got a rational map on the Riemann sphere. That's a P1. I use P1 for Riemann sphere. So it's rational with, it's not a linear fractional transformation or a constant. The degree is at least 2. Then there exists an invariant probability measure, mu, lots of properties, but I'm just going to home in on the one I want here. Okay, having trouble. There we go. Okay, such that for any point in the Riemann sphere that is not exceptional. So if you take the pre-image of Z, you don't just get Z back here. We have that if you start pulling back the Dirac delta mass at Z and normalizing appropriately by the number of pre-images, you converge to the measure mu in the sense of measures, all right? So this is so complex dynamics, if you think of it as a subject, is all about like figuring out what's going on with orbits of different points when you go forward. This theorem is saying if you go backward, then the same thing happens every time. All right, in a statistical sense, you always recover this measure. And I guess the other thing I should say about this is that the support of mu is the Julia set. Okay, so the subject is only barely getting started at this point. Now you want to, there's reams of papers have been written about the behavior of F on the Julia set, et cetera, et cetera. And the other thing you should take away from this is actually when you're pulling back point masses, which means in some more explicit way of writing things, you're just taking all the points, whoops, other way around, all the points W that map to Z, putting a little charge on W and normalizing, and they're converging to mu. So what you're really doing is finding roots of some list of polynomials and looking at the asymptotic distribution. And this fact right here is saying that the asymptotic distribution is very different than what you would get if you were just taking random polynomials to evaluate this distribution for. So that makes complex dynamics a different subject than just looking at random polynomials. All right, great. So that's dimension one. Now, dimension two. So if you've got a map from the projective plane to itself as rational, the correct thing to do is not use a solid arrow here because rational maps can be ill-defined at some points, but it's going to be a little bit careful with that. One thing you run into right away is that you have choices about what you want to pull back. You can pull back points. That's one kind of subvariety of the plane, or curves. Okay, so you can pick the dimension of the subvariety you're going to pull back here. Me and this microphone are not totally cooperating. Okay. Yeah, I'm going to focus on curves. But points are important too. So virtues of points, one thing is how many preimages does a point have? That has a name, that's the topological degree of F. And as with the dimension one case, if you start taking topological degree of iterates of F, that's easy. Just take the nth power of the topological degree of F. Points are especially important when the topological degree of F is, there's another degree, which will come out in a second, and I'm going to call it lambda of F. And that when topological degree is bigger, points are the most important things, in some sense. Okay. Okay, nevertheless, I'm going to focus on curves. So curves have virtues too. So in fact, they're interesting in all cases, preimages of curves, but they're more important when the other degree, which I have not yet defined, is the larger one. And if you have a curve, one virtue of curves over points is that they're more directly related to functions in some ways. If you're in algebraic geometry, they're defined by functions, but I'm going to take Eric's potential theoretic point of view. Then locally, C is like the Laplacian or the DDC of a plurisubharmonic function. Okay, you don't need to know definitions of all these things to appreciate what's happening here. It's this that you can directly think of C as some kind of distributional derivative of some function. Functions, even people who are used to working in the measures and currents world, I think will usually agree that if you can get away with using functions, you probably should. All right. I meant to illustrate that point even with the one variable equidistribution theorem. So let me go back to the one variable case for a minute. So this side of the board currently dimension is 1. Okay, how do you actually prove something like this? So how do you prove that? Well, here is, come along. Yeah. If you just pull back a point mass once by a one-dimensional rational map and you compare that with what you started with, this is always just the Laplacian of phi, where phi is, it's not smooth, but it has very mild singularities. It's like a difference of subharmonic functions. So it has log mod z type. Singularities. All right. So you can always write the difference between one pullback and the one before this way. And then when you want to do the nth pullback, you can just resort to some kind of telescoping series trick to compare things. So the other thing the thing that makes this effective is you can easily prove very, very mild estimates on how f acts on the volume of a set. So there exists constants. I need to rule something out. Suppose there exists no exceptional z in the sense that I hypothesized up there. Okay, I can easily eliminate this assumption, but it's easier to state the result. And there exists a couple constants bigger than 0, such that for every open set in P1 and for every n greater than or equal to 0, the volume of f to the n of u, map your open set forward. You just, in order to effectively use this fact, you want to know it doesn't get too small too fast. And fast means insanely fast. There's an n here, right? If you stop and think about what what violating this bound would mean, you realize that would be an impressive map that could shrink an open set that fast. Okay, and anyhow, you can prove it doesn't happen for a rational map of one variable. What that allows you to do is prove that when you start pulling back this function phi by your map, and then you're going to be normalizing by the degree of f. Here's, so a, b greater than 0, and b is less than the degree of f. That's a key point right here. B is not too big. When you start pulling back, the normalization completely kills the L1 norm of phi, and that's going to force this sequence to converge to something. And then you have to make sort of the same kind of argument to show that if you pull back 2 different points, you converge to the same thing. All right, that's all there is to it. Okay, so that's why it's good to be related to functions. Okay. Okay, great. So what can you prove? Quite a lot, really. Here's a theorem. Do I want to? So I need to make it. I'll do the definitions first. There are some terms to define. So a problem with curves, particularly if you want to use this argument again, is that this can be bad for rational maps. This normalizing factor can be bad. So we're back to some rational map on P2. You can write it in homogeneous coordinates as F0, F1, F2. You have 3 homogeneous components, and these will all be homogeneous polynomials of the same degree. And the degree of F is just, well, the other degree of F, which the thing which is distinct from the topological degree is just the common degree of these homogeneous polynomials. And if you like, it's the degree of the preimage of a general line in P2. Okay, and now the problem here is, let me illustrate, instead of telling you what, let me just illustrate by example. So suppose you have in affine coordinates, say x1, x2 is going to x2, x1, x2. This example never fails to impress me after all these years. That's a map in affine coordinates. In homogeneous coordinates, it looks like this. Actually, you can tell, and even in affine coordinates, the degree is probably going to be 2, but oh well. X0, x2, x1, x2. And now you iterate this map. A second time. X2, 2, and then you have x1, x2. So that's x0, x1, x2 squared. There, I did it. I haven't done this calculation for a while. And you notice what happens. There's an x0 in every coordinate. Okay, that you don't want. So the degree just went down. So in general, the degree of f to the n is less than or equal to the degree of f to the n, but equality needn't hold. Okay, so your normalization is messed up here. However, so at the very least, if you analyze this inequality just a little further, you do see that there's some asymptotic behavior. So this limit, as you let n go to infinity, of the degree of the nth iterate to the 1 over n, I should put some parentheses somewhere, but that exists. And in fact, I can pin down the range. So the least it can be is this, as it turns out, the square root of the topological degree. And then the sky is the limit. Okay, well, I guess no, the sky is not the limit. It's smaller. It's never bigger than the degree of f. So the degree can drop, but it can't go up over time. Great, good. So what are you supposed to do about the normalization factor? Well, a not unreasonable strategy is the following. So definition, we say f is algebraically stable if there does not exist a curve that gets contracted to a point. That can happen in dimension 2. Curves can just collapse. Okay, that's okay. That's not a problem. And then as you map that point forward, you end up in what I almost always call I of f, which is the finite set of points where this rational map is not well defined. Okay, so in pictures, failure of algebraic stability means this: curve is contracted, maps forward, maps forward, maps forward, maps to a point which doesn't, properly speaking, have any image, but just blows back up to curves. Okay, so if that doesn't happen, you say it's algebraically stable. And so how to say the next result? I don't want to overdo this. As well, it can happen. It's easy to come up. Well, I just gave you an example of a map which is not algebraically stable. You can analyze it yourself, but we're going to generalize a little bit. We say F, or actually, let's not mess around. This is my own word for the day. I say F is stabilizable if there exists a finite sequence of blowups. So strictly speaking, birational morphism. Pi from some other complex surface down into P2. So you kind of, you take some points and you replace them with curves in P2 such that F lifts to an algebraically stable map on the surface upstairs. Okay, so this is this, as it turns out, is a good thing. Okay, and it implies that so what takes the place of the degree upstairs? What it takes the place of the degree upstairs is that you have this pullback operator on, let's just say, the Picard group of X. Let's save a little space there. So even though it's not a well-defined map, you can pull back divisors, you can pull back curves, whatever. And it has the property that you can pull back n times, or you can pull back by the nth iterate, and it's the same either way. Okay, that doesn't work if you're not algebraically stable. Okay, so this is a good thing, and it is in particular good for the normalizing factor in the one variable, if you try to bring in the one variable argument for equidistribution. So this is the map on X. It implies that downstairs, this sequence satisfies a linear recurrence relation with integer coefficients. So in some sense, you can write down all the degrees fairly easy, and you know how to normalize when you pull back. Okay, so that's great. With all that in mind, I can finally state my second theorem from about 10 years ago. Myself, Dujardin, and Gedge, which says, well, which can be made to say, if you sufficiently massage the statement we gave, let F be a stabilizable map on the projective plane. Be stabilizable, yeah, that's a problem with this term. Stabilizable, then there exists not a measure anymore. So the other thing about this, curves do not naturally define measures. They don't pair, you can't just take a function and integrate it over a curve in P2. Instead, what you have to do is integrate a form over a curve. And once you remember that, you're led pretty quickly to the distributional equivalent of a measure, which is a current. specifically a positive closed current. I should probably keep calling it mu, but I'm so much in the habit of calling it T that I'll stick with this. There exists a positive closed current T star such that for almost any curve, in P2, we have equidistribution. F to the n star C over the degree of F to the n converges to T star as, I guess I should say, as n goes to infinity. This is the exact analog of the theorem I stated in one variable for curves, not for points. There's another theorem like this for points, which, yeah, sure. Yes. Oh, off the top of my head, no. And I think in general, it's probably not true. So I'm thinking, but I don't want to commit to that statement at the moment. Yeah, it's a good question, right? Is it just equivalent? Yeah. So I have an example in mind that I can try out with you after the talk. Yeah. Okay. Any other questions so far? I love interruptions. Most of us do. Yeah. Okay. All right. So that's great. Let me just hasten to add. That's a hypothesis, and it's real, as I'm about to point out. I mean, it's not true all the time. And then there's also this peculiar almost everything anymore. There's not very specific about which curves are exceptional here. And that's an artifact that comes from the way we prove it. All right, so let's see how much further we can go with this. There's a specific kind of map that is a problem for this theorem. So here's like a big class of examples. So if you have a 2x2 integer matrix, this gives you a rational map as follows. A rational map, which I will call monomial. And it's given in affine coordinates by surprise monomials whose powers are determined by the matrix. Like that. That's a monomial. Well, what could be easier than that? That first example I gave you, though, that was a monomial map, that one that was not algebraically stable. So not only do monomial maps not have to be algebraically stable, let me make sure I'm not forgetting something. Yeah, they don't even have to be stabilizable. This is an old observation of Favre. So if the eigenvalues of A are complex conjugates, zeta, zeta bar, where they're not like I or something like that either. They're not like plus or minus I, but they're, all the powers are complex too. So zeta to the n is not in R for every n greater than 0. So the argument's irrational times 2 pi. Then HA not only is not stable, it's not stabilizable. Okay, so you're never going to be able to write down the, or you're never going to be able to apply that theorem to that map right there. Okay, nevertheless, I mean, there's something why would you want to apply that theorem to this map? Because this map should be analyzable by hand. You can do the dynamics because it just comes from a linear transformation on R2 with integer coefficients. Okay, so nevertheless, you can solve the equidistribution problem or answer the question by formula. You can write down an explicit formula for T star associated to the map HA. And I want to make this point in spades right now. So I don't want to have to conjugate my matrix. So I'm going to let me state a successor theorem that really underlines that one. So more recently, Bell and Janssen and I showed that if you take that zeta in Fob's theorem to be just a Gaussian integer, and your matrix A to not be just any matrix with eigenvalues zeta, zeta bar, but let's make it the one that actually corresponds to multiplication by zeta. Okay, then not only do the degrees not satisfy a linear recurrence, then lambda of HA is a transcendental number. Oh, sorry, no, I'm getting way ahead of myself. Not yet, not yet, not yet. I'm not ready to finish this theorem yet. Sorry, this is what happens when you offload your head to slides and then try to put them back the last second, but I can complete this later. So anyhow, with this A, the T star is just, so on, not on the entire space, but just on P2 with all the axes in the line at infinity removed, T star is very, very simple. It's DDC magnitude of L of X1, X2, here, I don't even need to write it that way. Log mod X1, it's standard to put a minus sign there, log mod X2. Okay, this is it. This is a formula for the equidistribution current. You can check, if you like, that it's the right one, at least on C star squared. Although from the current point of view, this one's really bad. If you know anything about Lalong numbers, this one is has very strange singularities, even though it's got a simple formula. Okay, so I need to return to that theorem in a little bit. What's that? That's right. So you take your complex numbers, you take negative log mod each of them, and that's a point in R2, and you take the Euclidean norm of that point. It's not a standard looking thing from a pluripotential theory point of view. Not really, but it is sort of like there's a paper with Junho and Babahi where they are very meticulous about putting the mice, and I am not going to take issue with them over this. So no, but it doesn't matter here. Yeah. It is a Euclidean norm. So what's really going on here is there are toric surfaces underlying this whole thing. And what I'm doing is turning a point in the torus to a point in one of these, in the like N sub R, you know, one of the realified version of one of the lattices associated to toric surfaces. So, but I mean, it's natural, is all I'm saying from a certain point of view. Okay, how am I doing? Yeah, with slides, this would move along a little faster, but okay. Now, this is the point where I always have to warn the audience. I'm going to write down a map, and it's going to come out of nowhere. All right, here it is. This is what I needed to complete the statement of that theorem up there. So you have an involution that is not monomial, but somehow, in some loose way, it is related to monomial maps. You have an involution, G, from P2 to P2, given by again in affine coordinates, x1, x2, so far so good. And then it goes bad. Actually, still so far so good. It's the extra stuff. 1 minus x1 minus x2, 1 minus x1, 1 minus x2, and it's the numerators are slightly different. X2, okay. No reason you should like this formula. No reason you should believe without checking that it's an involution, but it is. You take G squared, it's the identity map. Okay, and it's easier to remember the picture. This is projective space, right? Maybe the x1 or x1 axis, x2 axis line at infinity here. Infinity. And the way this involution works, there's a kind of standard quadratic transformation, standard involution on projective space, which just involves taking reciprocals of both affine coordinates. This is that, just in other coordinates. And in particular, there is another triangle. What's important about it is the vertices are on the axes like this. And the map just takes one side of the triangle and sends it to the vertex on the other side, collapses it, blows the vertex back up, and so on. Okay, I made my picture too small to put the third arrow in here, but it just exchanges sides and vertices in some triangle and then switches them back if you apply it again. So that's geometrically what this map is looking like. And now I can conclude. Oh, I knew the talk, I knew I did nonlinear dynamics, but the talk is peculiarly nonlinear today. So anyhow, so then, the map F, which is the monomial map HA for this matrix A, composed with that involution. And just like in Favre's theorem, it remains not stabilizable. Okay, in fact, that's not the content of the theorem. We knew, so Jan Lee Lin and I knew this some years before this theorem was proved. We knew that, and it's not stabilizable for the same reason which I haven't given for the other map. So what's new is that in this case, the lack of stabilizability stands out. Because that lambda, that dynamical degree, is a transcendental number. Okay, so it's a little worse. All right. It's the same condition as in Favre's theorem. I didn't rewrite it. Yeah, that no real powers or irrational argument. Yeah. Okay, so that's the theorem. Right. So now I think I can finally get to the new theorem. Or actually, I need to say one more thing. Something that might make you feel a little bit better about that map G. Okay. Both G and any monomial map HA are what I've been calling toric. I'm in the market for some better terminology, but absent that, we'll use this term, are toric, i.e. F, or this is the definition, is toric if you take a particular holomorphic 2 form on C star squared, and when you pull it back, you just get a multiple of itself. All right, this is a kind of a canonical 2 form on C star squared, although it's just written down in coordinates. I'll call it eta. And being toric means you preserve that 2 form up to constant multiple. All right. Now you can check for yourself. It's not so surprising that the monomial maps are toric. And the particular constant's the determinant of the matrix. But if you just do a hand computation, you can check that G is toric too. And the constant there is 1. Okay. So, and it's pretty clear from my definition. Well, after I've told you to worry about composition, suddenly nothing seems clear. But pulling back forms is good. So if you have 2 toric maps and you compose them, you get another toric map. So the map in this theorem, HA composed G, that's also toric with the same, with this for its delta. Okay. So here is, at least I get to state the theorem. A theorem that Roeder and I are busy writing up right now. So if F from P2 to P2 is a non-stabilizable toric map, such that there's another hypothesis that I'm not going to write down. Maybe the only thing I'll say, right, I probably won't even get around to writing it down. But as far as it's satisfied by all the examples of toric maps we know. Okay, so I don't know any violations of the hypothesis. If it's a non-stabilizable map such that blank, then there exists a current, a positive closed current, T star on P2 such that for every curve C, no almost every anymore, just for every curve C in P2, we have such that I'm, again, this is a problem with going from slides to talks, such that, let's write this down in 3 steps. T star does not charge curves. In other words, the most singular kind of positive closed current you can have is a current of integration over a curve. T star doesn't contain anything like that in it. Secondly, when you pull this current back, whatever pullback means, you just get the dynamical degree times the current. But you got to be careful about pullback in one sense. You might, when you pull back, pick up some spurious curves, and you want to obviously throw those out if you get them. So modulo curves. And finally, 3 is that for every curve C in P2, we have equidistribution. Okay. In particular, this theorem applies to the map. Where did I already erase? No. Applies to the map in the theorem with Bell and Janssen. Okay. But it applies to, I mean, once you see this, it may look like a theorem about a very particular class of maps. But let me point out now, you can just build up toric maps by composition. You could take that factor G, you could take a monomial map, you could compose it, you could keep building up things like this, and you get a whole semi-group of things. And furthermore, almost all the examples we have of non-stabilizable rational maps are in this class. Until recently, all the examples we had in this class. But recently, my graduate student found another one in the world of skew products. And that's the one I was going to use to try and answer your question from earlier. You had another question, though? No, it's every curve. It's yeah. So the difference between let's see, yeah, there's a so we prove this theorem using what are in some ways better techniques than the theorem with Dujardin and Gedge, and so you get to replace almost every with every in the end. Because in Dujardin and Gedge, the theorem with Dujardin and Gedge, we kind of dodged the whole issue of volume estimates. Oh, you mean you have to throw out the whole pre-image? Yeah. Is that the question? Yeah. So the second one is only applied to T star. And that's why I stated the first one, because the second one makes no sense until you know that T star doesn't charge any curves. Now, I don't want to work modulo curves down here for exactly that reason, because if I work modulo curves, this is 0, right? So it's only, yeah, Eric? I mean, necessarily non-stabilized. It's okay. We're getting to the part where I wave my hands like crazy here. So there are definitely stabilizable toric rational maps, and so for those, Jan Lee and I proved. Jan Lee and I classified. We gave what I think is a nice criterion to distinguish between stabilizable and non-stabilizable ones. Our proof only applies to the non-stabilizable one, only applies to the ones that the theorem with Dujardin and Gedge do not. Things are in some sense actually better if you have something playing the role of this matrix, which introduces an irrational rotation into the picture. It allows you to average some things out as you go, and good for volume. Good for volume. Yeah. So I mean. Anything else at the moment? I'm not going to say everything I had to say. Yeah. Oh, I'm sorry. I just didn't hear it. Oh, no. You get the current is totally dependent on the choice of the matrix A, implicitly on the choice of the angle theta. I mean, I would be stunned if somehow you can. There's no zeta in. Oh no. Okay. Sorry. Okay, I've thoroughly messed things up. So on C star, let's take this away. This is the equidistribution current. I understand your question much better now. For the monomial map. Okay, if this is your matrix and you take the monomial map, then you really do get the same current, although independent of the matrix. It's just kind of uniformly spread out somehow, at least, especially when you look in these log coordinates here. But for these maps and this there, for the F, no idea. I mean, we just have an existence theorem for the current. just say, let me write down some sort of cryptic lines in lieu of a proof of this. I think I'm at least as excited about just the sort of technical aspects as I am about the statement of the theorem here. But I'll reiterate, these are basically all the non-stabilizable maps in dimension 2 that we know of. So ideas in the proof. Okay, first, you consider the map and the theorem not on P2, but as a map between various toric surfaces. Since I haven't defined toric surfaces, I'll put it in quotes. But suffice it to say that a toric surface is a certain kind of compactification. Of C star squared. So you throw out the axis, or it looks different than P2 only in where the axes line at infinity used to be. Okay, so in fact, the set of all toric surfaces forms a nice partially ordered set, forms an inductive set. So you don't just consider it as a map between various toric surfaces. You consider it as a map between all of them all at once. All right, as a map. Since I'm out of time, I can put a hat here. On the inductive limit of all toric surfaces. Okay. So what you do then is on this inductive, I mean, this is just some weird space. It's not like some algebraic variety or something like that. But you could, it's still meaningful to kind of talk about cohomology classes or classes in the Picard group. So in there is some notion of a Picard group here, and a pullback on the Picard group and so on. So you can still talk about that and prove an equidistribution result for classes. In fact, we didn't do that. That was done by Buxom, Favre, and Janssen. We just like particularized their theorem. Really, most of the credit goes to them there. Nearly all. Okay, so Janssen is the intersection between these two groups of 3 authors there. And then there are 2 other pieces. So one is on this inductive limit, not only can you talk about classes, you can talk about positive closed current. And you can single out some natural ones that uniquely represent they have a lot of symmetry, so they uniquely represent positive classes. Okay, and then finally, you prove volume estimates for forward images of an open set and a toric surface, any toric surface. Okay, you prove volume estimates. And it's in this last place where you really, really use the fact that the map is not stabilizable. So something or other turns into an irrational rotation, and it really helps smooth your way when you do the volume estimates here. So let's see. Yeah, 5 till 3. Be a good time for me to stop. Thank you. No, I think that's not an unreasonable hope, particularly. So I don't know, like the construction they use formally makes sense in any dimension. And you're right, you want to pick on hypersurfaces, not curves. And you could do this, but what would give me hope here, and if you're going to do something in dimension larger than 2, let me start by wishing you a lot of luck. But because that always intimidates me. But this restricting to just toric K folds should help quite a bit in higher dimension, because that's a much more concrete thing than just letting yourself do any blow up whatsoever of a high dimensional. Yeah, so that should be not so bad. Is there some piece that I mean, it's not an unreasonable thing to try to generalize this to higher dimensions. Probably you end up imposing a hypothesis somewhere, but you know, you've done more than anybody before you. Yeah. Yes, Lucas. Oh, yes, right, such that. Okay, you asked for it. What is the easiest way to say this? I'm gonna say it in a way that afterwards I'll say it in a way that sounds entirely different if you like, but let's just see. So at the moment, all known examples of toric maps on P2 are in the semigroup generated by monomial maps and maps like G, that is birational, invertible toric maps. Maybe not involutions, but okay. What makes the semigroup interesting is that there's so many birational ones. They've been sort of understood. The whole structure of the group of birational ones by Jeremy Blanc has a nice paper about this. But so all the known examples are in the semigroup generated by these two things. So one way I could fill in the blank is I could say such that F is in this semigroup. There's another way to say it, which I like better, which is more like a condition on the matrix A, but A gets replaced by something else in here. Something or other is a homeomorphism. And it's a priori weaker statement than this, but if this is true, then certainly that is, I mean, if it's true that this is all the examples, then that'll be true too. Yeah, 2 yen. Yes. The class in, so T star, really is more naturally occurrent on this space. And in this space, it has a class. There is an invariant. There is a class which is somehow pullback invariant by this thing on this space. That, I mean, what I'm saying is vague, and saying things vaguely makes them sound hard. It's not terribly hard, but it does have a class in this kind of infinite dimensional Picard group here. Yeah, good question. I mean the smaller of the two. It's always somehow smaller to pull back by f to the n than to iterate f star n times. Yeah, I still want lambda of f to the n, but I don't want degree. Or well, if you like, you could just put so asymptotically, the degree of f to the n is lambda of f to the n, not the degree of f to the nth power, but lambda of f to the nth power. Yeah, it gets right, a lot to keep track of. So, but I could state it that way. What I don't want to do, it's really important where you put your n's in your parentheses here. Yeah. Yeah. Yes, that's true. No. It's not stable on P2. But if the matrix has real eigenvalues, which is about as likely as having complex conjugate eigenvalues, then it is stabilizable. Favre's theorem is actually an if and only if. So the monomial map is stabilizable if and only if the eigenvalues of that matrix. Yeah, okay. I don't know the answer to that question, but again, so this is actually related to Lucas's question. So let me just say something again, a bit cryptic here. So for a monomial map, there is this map A, this matrix A on R2. For a general toric map, you have something like the matrix A. There is, and it's a map on R2. Okay, but R2 is not R2. If you study toric surfaces, this is n tensor R, where n is some lattice in the definitions. So there's a map which I call A sub f, and it is so the way A sub f works, it's not a linear map anymore. It's linear if you start with a monomial thing. It's linear for the map in that theorem, but in general, you have a decomposition into cones in R2. And it's linear on each piece separately, and it's continuous as a map on all of the space. Okay, so another way to frame that hypothesis, and somehow it keeps track of what's going on. This map helps you keep track of what's going on outside C star squared, the part that is kind of is up to you in a toric surface. Okay, so somehow it helps you keep track there. And so another way to fill in the blank is to say that AF is a homeomorphism. So it's always in some sense like a covering map of R2 minus the origin, but we don't know it's always a homeomorphism. It's really an annoying thing. I mean, it probably always is, but I don't know. So whenever it is a homeomorphism, it has a rotation number. Because you can just sign a quotient out. You can think of it as a map, a circle map, by just like quotienting out by positive scalings. Okay, it has a rotation number. And so what Lynn and I showed is that F toric, this business only works for toric maps, is stabilizable if and only if the rotation number of this thing is rational. Okay, so it's a rotation number of something. It's just not a strictly linear thing anymore. It's hard to get your hands on in general. So that's a non-answer to your question, but yeah.
All right, excellent. So
Yes.
yeah, thanks so much for having me, and I'm sorry I couldn't be there in person. It's just a little bit hard to travel right now. We also have a young baby, so that makes it like especially hard in addition to the pandemic. But yeah. All right. So I want to talk about on dynamical cancellation, and so this is joint work with. So this is joint with Jason Bell and in Yosuke Matsuzawa. Okay. Oops, sorry, I always mix up. There we go. Okay. So the idea here, I want to start off with just a very simple example, and just to begin with. And so the idea is, if we start off with, say, if I start off with a rational number, and I tell you, I mean, this is kind of a somewhat trivial example, but if I tell you x to the 2 to the n is 1, and then this implies that, well, x is equal to plus or minus 1, right? And so another way of saying that is just that, so equivalently, that x to the 2 to the 1 is 1, right? So, and that's not special to Q. You could deal with a number field. I mean, so the same is true for a number field. If I give you x inside of K, which is a number field. And x to the 2 to the n is 1 for n sufficiently large. Then we also know that x to the 2 to the m is 1, where m is just some fixed number that depends on the number field. M is fixed. And it's not a mysterious reason, it's just that there are finitely many roots of unity inside of the number field. So this is because K has finitely many roots of unity. Okay, but this would definitely fail, say, if you're looking at the complex numbers, right? You know, so that if x to the 2 to the n is 1, where n is very big, that doesn't say that you can cut down that n and make it smaller. All right, so we're at a dynamics conference, so we can rephrase this dynamically if we want. So we can rephrase this dynamically. So you can view this as a map that goes from P1 to itself, which sends x to x squared. And we're saying this kind of somewhat weird thing, which is that if I've given you y, which is the point 1, that's a subvariety of P1. And then we say that if I look at the inverse image under y, well, that's just all of the x's such that x to the 2 to the n is 1. And we're saying that over a number field, if you're in a pre-image for n sufficiently large, then in fact you were in a pre-image of y for n much smaller. So we're saying that if x is in Fn of y for n very, very big, and x is k point, then in fact, X was in a much smaller preimage. Just depending on the number field. All right. So there was really nothing particularly special about the squaring map and about Y being this particular point. And this falls under a question that was raised much earlier, or a few years ago, which is this preimages question. So you could just consider the setup, where you have X being a projective variety. Over a number field. So K will be a number field. I'll probably stop writing that at some point. And I give you a map, which is search active, defined over K. And I give you a subvariety, and we just want one thing, one condition on this, which is I want to make sure that f of y is contained in y, right? So for our case previously, we had that 1 squared. If I take 1 squared, it's still 1, so it's a fixed point. And the reason you want that is because that's going to imply that, well, that y is contained in f inverse of y. And similarly, this is contained in f -2 of y, etc. So we end up with this gigantic tower of preimages. And so, you know, we're in this kind of, we're all very familiar with this kind of dictionary that geometry and arithmetic kind of go hand in hand. And we expect that geometrically, this tower is going to become more and more complicated. So we expect geometrically the preimages will become more complicated, more and more complicated. And so that should have an arithmetic incarnation. And so the arithmetic incarnation here is that the rational point should stabilize. So, so arithmetically, we may expect stabilization. So, so specifically, there was a preimages question that was raised by Yosuke Matsusawa, Meng, Shibata, and Jung. And so they asked, you know, is it true that there exists some number S naught, just depending on the setup, right? So depending on X, F, and of course the number field, such that for all S bigger than or equal to S naught, the S preimage the K rational points of the S preimage are contained in the S naught preimage, K rational points. So that was their question. Okay.
Question for the audience.
Yeah, go for it.
They're asking if should this be true for any y, or it depends also on y. It's not.
Sorry. Yeah. I think so. They did state sort of stronger versions of this, but no. So yeah, thank you for pointing that out. It does depend on. Yeah, thanks. Okay, thanks. Right. They also did state a stronger version where they allow the number field to vary. But I just want to concentrate on this one version here. So for the most part, this talk is going to concentrate on a special case of their question. But I'll just state one thing that we can prove that Jason, Yosuke, and I proved about this question over here. Which is that, so if X is a smooth projective variety, and F, well, okay, so this is, and the Kadir dimension of X is at least, non-negative, then the answer to the pre-images conjecture question is yes. And really, this wasn't a statement about Kadir dimension. It was really just a statement that we showed this for étale maps. So more generally. But if you have non-negative Kadir dimension, then and under those conditions, that forces F to be étale. So okay, so it shows that the question is going to be, you know, the interesting case is really when you're dealing with negative Kadir dimension situation. And the proof here uses p-adic local methods. But the real case that I want to concentrate on is a special case of their pre-images question, which I don't know, I found kind of fascinating. Well, we found kind of fascinating, and so because it captures a wide situation, wide variety of situations. So the way it's going to work is we're just going to say let Z be any smooth projective variety. You know, over a number field, etc. And we're going to take G to be a map, you know, just surjective. And we're going to consider the situation where X is Z cross Z. And where Y sitting inside of X is going to be the diagonal. And under this situation, if you take F to be G cross G, then that goes from X cross X and it automatically preserves the diagonal. So then F of Y is contained in Y. So we're in the setup that they care about. But here the pre-images question kind of has a nice form. which is, so if you look at what's f inverse of y, or f to the negative n of y, well, I mean, so this is just asking what are the points x comma y, which are in z cross z, such that f to the n of x is f to the n of y. And so the preimages question takes a form of kind of a dynamical cancellation. So we just stated this as a conjecture because we actually, there's not much of a difference between stating it as a question like they did, but we felt that we got enough of a feel of this case that we felt like it should be promoted to a conjecture. So I'll just call this the dynamical cancellation. Conjecture. Which is that, so this can be rephrased. It's again a special case of their question, but so this says that that for all s, if f to the s of x, if s to the f of y, so these are rational points, right? Sorry, actually, I want to say there exists. So there exists some S naught such that for all rational points and for all S, if f to the s of x is f to the s of y, then f to the s naught of x is f to the s naught. All right. So you have this cancellation, which says that you can kind of cancel these f's in order to get down to a smaller power. All right, so so you'll notice in their question they asked about the projectivity assumption. They have a projectivity, a projectivity assumption. Sorry, I think that was a setup way back here. And so for this dynamical cancellation, for example, you do need projectivity. So let me first give you an example where to show that projectivity is necessary. Okay. And so the example, we're going to take X to be affine space. Oops. Affine 2 space. And we're going to cook up an example, which is going to send xy to xy, x squared plus xy. And well, we could rewrite that as x times y, x plus y. And we're going to build a sequence out of the Fibonacci number. So let Fn be the nth Fibonacci number. Where f naught is 0 and f1 is 1. So that's the conventional one. Okay, so the sequence we're going to look at is we're going to let a sub n be fn negative fn minus 1. And let's see what happens when we apply our map. So that's going to be, well, it's Fn times negative Fn minus 1, Fn minus Fn minus 1. And so, that's Fn minus 2. And so this whole thing becomes Fn, well, I'm going to pull out a negative. So Fn minus 1, negative Fn minus 2. And so we've just decreased the sequence. All right, so if we iterate n times, we're just going to get plus or minus the product of all the Fibonacci numbers. Oh, no, not F0. So F1, Fn, and then times A naught, which is 1, 0. And I actually want to apply F 2 more times to see something interesting happen. So if we do Fn plus 1 of An, well, that's this, F of 1, 0. And F of 1, 0 is 0, 1. And so this thing is still non-zero. That's kind of the point. So if we do F to the n plus 1 of An, it's non-zero. But if we apply it one more time, let's just go back and take a look at our map. If we apply it one more time, we're multiplying by x on the outside. And so since we have this 0 in our x coordinate, it's going to kill this point. So if we do Fn plus 2 of An, then we're going to get 0, 0. Okay, so just to summarize what we have there is we see that if I take f to the s, and s is bigger than n plus 2, then you're always going to be sent to 0. But if we do f to the n plus 1, then it's non-zero. Okay. So in particular, if we do f to the n plus 1 of An, that's not 0. Well, so f to the n plus 1 of An is non-zero, but f to the n plus 1 of An minus 1 is 0. Okay. So, so what we have is we have these two things that are not equal to each other. F to the n plus 1 of An is not equal to f to the n plus 1 of An minus 1. But if I hit it one more time, then they both go to 0. But f to the n plus 2 of An is equal to f to the n plus 2 of An minus 1. So we have this infinite sequence of things, this infinite sequence of distinct rational points, so that they're, if you hit them with n plus 1 iterates of f, they're not equal, but n plus 2 iterates, they are equal. And so this shows that the rational points don't stabilize. So the k rational points, well, in fact, the q rational points, so dynamical cancellation fails for this particular sequence, right? So that's the point. Here are the q points of A2. There's no S naught that you can choose because you keep having to ratchet that S naught up higher and higher. I don't know if there are any questions, or feel free to interrupt if there are.
Matt, can you hear me?
Yeah, of course, yeah.
Can you go back to your dynamical cancellation conjecture, the statement?
Sure.
Yeah, so here you say for any xy and for any s, if this is true, if what is for any s, those points satisfy. If f is s is 0, then that means that these 2 points are the same. Do you need s really need s is greater than or equal to 0, or s is sufficiently large?
Oh, I guess it's kind of a silly statement. If s is less than or equal to s naught, then it's a silly statement, right? I mean, like if f of x equals f of y, you just keep hitting it with powers of f until f of s naught equals f of s naught of y, right? This statement is equivalent to saying if s is sufficiently large, then this is true.
Okay, thank you.
Yeah. But you're right. The content is if s is sufficiently large, then this is true. Okay. So one of the things that makes this dynamical cancellation a little bit tricky is, so if you remember, I said that for the preimages question, that the case that we handled, the étal case, or the Kadar dimension, the non-negative Kadar dimension case, the case that we handled there, we are able to use p-adic local methods, but for the dynamical cancellation statement in general, you can't. And so kind of the second example, which I'm not going to go into any detail, but I'll just write down the example, is, so unfortunately, p-adic local methods don't suffice to handle dynamical cancellation. Okay, and so I'll just write down one example for you, is that you can write down the specific map on P2. So it's kind of the simplest possible map that you can imagine for surfaces, which is just, and it's just going to be given by quadratics. So you can't really look at linears, that wouldn't be good enough, so you have to look at quadratics. And so on a surface. So in this case, then what happens is, then for all P, for all primes, including 0 and infinity, dynamical cancellation fails. Yeah, dynamical cancellation fails in QP. So it's just not good enough. You can't just, like, you know, choose a good prime and consider a model and then just try to reduce to a local statement. Okay. So what we can prove is that cancellation holds for curves and, you know, one of the things about this is that even though it's stated as dynamical cancellation for curves, it's you know, secretly a statement about surfaces, right? And I think that's part of the complexity here is that, so when you try to prove, if you try to prove dynamical cancellation for surfaces, you're secretly proving a statement for fourfolds, right? You're considering the pre-images conjecture for fourfolds, a special case, of course. So the case for curves isn't completely obvious, because you get into these kind of very thorny issues where what you're dealing with is you kind of have to address a question like the following. So first of all, because we handled the Kadar, the non-negative Kadar dimension case, what really you're just left with P1 here. So the content is, so because of the previous theorem, just need to handle the case of P1. But you run into these kinds of issues where you have a map like a polynomial, and you want to know, so if I've given you, say, a polynomial, this is the kind of issue that you're going to run into. So what is the pre-image of the diagonal? Well, you're writing f of x minus f of y, but you don't want to consider the rational points of the diagonal because we're talking about stabilization. So you want to divide this out, and you have to deal with iterates of this kind of thing. And you want to know, for example, when does this have genus 0 components, or when does this have genus 1 components that happen to contain infinitely many rational points? So you need to understand issues such as when does this have genus 0 components? But not only that, right? Under iterated pre-images. Okay, so we can actually show a little bit more than this, which is we can also show a multi-map version of this. So it can also multi-map version. So, you know, i.e. a semi-group that you're considering. Okay, so before I just state that, let me just, you can consider the following question. So does there exist and not such that for all AB in P1 of K, Great. So first fix a finite collection of polynomials phi1 to phi r. So these are polynomial maps from P1 to P1. And then you could ask, does there exist an n naught such that, so now rather than just considering iterates of a single polynomial or rational map, then you could ask, now I'm allowed to just choose arbitrarily which phis I'm choosing, and can I cancel out a whole bunch of them? So does there exist an n naught such that for all a, b, and p1 of k, if phi I n phi I1 of A is equal to phi I n phi I1 of B, then I can just cancel out and be left with phi I and not phi I1 of A. Okay, so this question is too strong. Like that would be kind of maybe the first guess that you would have about a multi-map generalization. But so this, the answer to this is no. And so you can, in the reason why is you can consider things like let phi 1 be any even polynomial. And phi 2 an odd polynomial. And then what we would see is that if I look at phi 1 of phi 2 to the n of A, well, that's the negative, oh, sorry, of negative A. The negative pops out, but then phi 1 kills that negative, right? So we have phi 1 of phi 2 to the n. So this is true for every single A. So you have infinitely many rational points where you can only cancel out one phi from both sides. So this shows that you need to allow for some kind of exceptional sets, or you have to allow for some kind of exceptional maps. So either need exceptional sets of k points, or exceptional maps. And you could consider both kinds of questions, right? Right. So let me consider the exceptional map question. So we're familiar in dynamics that the kinds of maps that tend to have exceptional behavior, things like monomials or Chebyshev maps. So and so an even polynomial is really, it's a squaring map, right? Up to linear factors. It's a squaring map. And so we want to kind of discard that as an example. So if I give you phi being a polynomial of degree at least 2, we're going to say that this is exceptional. If over the algebraic closure of K, it has an indecomposable factor of the form L1 composed x to the n L2, or L1 composed an odd Chebyshev. So the LIs are linear maps. So we're just saying, you take your phi, you decompose it in terms of composite factors, and then if up to a linear change of coordinates, you see a power map or an odd Chebyshev, then we're going to say discard this guy. And then from that point of view, so if phi 1 to phi r are not exceptional, then you still do need an exceptional set of rational points, but it's only finite. Then there exists a finite set So Z is a finite set. Such that for all A and B rational points, for all A and B not inside of Z, and of course they're rational points, so all A and B then if you have n compositions applied to A versus n compositions applied to B, then in fact you can cancel all but 2. And the exceptional set is unavoidable. Because you can just choose, so you can choose P and Q polynomials that satisfy some constraints, but they're still fairly general. And A and B rational points, where you have A, you have B, and P is just going to bounce you back and forth between these. So you just do a bunch of iterates of P, you're just bouncing back and forth, but then Q collapses you to some particular point. And then with the setup, then you have that if I take Q applied to P to the n of A, that's still going to be Q applied to P to the n of B. So it's like the even odd example, but it's so that the even odd example was on an infinite set that you had exceptions. Here it's just on a finite set, but you still can't avoid it. So maybe just I'll say a couple words, but I'm not going to get into any details about. So the rough idea. Oops. Sometimes it just doesn't let me write for some reason. Okay, so the rough idea of the proof of cancellation Oh, actually, when am I supposed to stop? The next talk starts in 7 minutes.
Yes, but since you started late, I think you had 15 minutes, something like that.
Oh, okay. Well, I'll just say a few sentences about this, and then I'll leave it so that there's enough time for the next. So I'll just say a few steps. So the rough idea of the proof of cancellation for curves, which is really just P1, right, is you do use some local methods in this case. So kind of step 1 is you reduce to the p-adic local case. You reduce to a dynamical cancellation. Statement over QP, right? So you just have a map. So even though the full dynamical cancellation question you can't attack using p-adic local methods, in this case you actually can. And so then step 2 is now what you do is you choose an iterate such that, well, you can look at F bar which is a map. And I actually just want to look at the FP points, not the map. And you choose n such that Fn bar is the same thing as Fn bar to the n is the same thing as Fn bar to the n squared. And the point of this is that if you let G be F to the n, so now that's a map on QP, and the point is that this preserves and you find, and this is chosen, and you can show that this is actually just an easy claim. You can show that if I give you two ZP points, and it happens to be the case that F, just an arbitrary iterate, F to the n of A equals F to the n of B, then F to the n of A, this capital N, the one that we showed, if I just look at these as FP points, then they're equal to each other and this is a fixed point. So the point of that is it says that, so with dynamical cancellation would mean we want F to the capital N of A to equal F to the capital N of B. Well, we don't know that, but we know that their bars are equal. So we know that when you view them as FP points, they're the same. But the point of this is that then this map F to the N, which we call G, preserves a p-adic neighborhood. So G preserves the p-adic neighborhood up to a change of coordinates. Well, the D of C, comma 1. So it preserves this ball. And then step 3 is then you just have to prove a statement about p-adic neighborhoods. And so you use p-adic uniformization. And you just need to analyze. There are a few cases that you need to analyze. And that's kind of where the work goes, is you need to analyze this map. Well, G can be viewed as a power series. And you need to analyze all the different cases that can show up from p-adic uniformization. So, all right, I'll stop there. Thanks.
Thank you. Are there questions in the audience or online? No, apparently not. So let's thank Matt again. Ah, okay, sorry. Sorry, there is one question. It was very behind.
Can you say a little bit about how you prove in general for the case of codiagram dimension non-negative?
Oh, yeah, well, let's see. So I forget a lot of the details at this point, but it almost becomes a topological statement in the end, which isn't like too surprising because it's in a tall map. But so you end up looking at a model, and I'm not sure. I thought I was going to open my mouth and the words were going to, no, but I don't think I remember the details, but you end up having to No, sorry, I don't think I can recall, but I can send you an email if you if you write me. Yeah.
We have another question.
I'd like to ask one question. You gave some outline of proof for P1 case, and which part is destroyed if you consider higher dimension?
Oh yeah. So
P2,
this
P2
is,
or P3?
yeah. So this is, if we go back to this example that I mentioned. Yeah, this one. So you just kind of lose at step one. Is really you can spread it out to a local model, right? You can try to do a local model, but for this specific example, dynamical cancellation is actually just going to fail for all possible terms.
Then which part is most essential for P1?
Well, I mean, for P1, we're really using p-adic uniformization in the end. So we have a lot of structure about what the about what it looks like on these open neighborhoods, right? You can divide up into cases depending upon whether the map is attracting or super attracting, and yeah.
And
so that's kind of the hammer that we hit it with for P1.
Sorry, and for non-negative codial dimension case, for example, especially for kappa 0 case, result follows from Bogomolov decomposition.
Oh, for Kadar dimension 0? Yeah, I mean, it's possible. I mean, we didn't think about that because we were able to handle the more general case, right, of the pre-images question. But there's probably a good chance that it does.
Thank you.
Yeah.
Thank you very much.
Sure.
Okay, so we can start the last talk today. Joerg Winkelmann is going to talk about quaternionic function theory, a Picard theorem. Please.
Okay. It's already on? I see. Yeah. Okay. I'm happy to be once again in Italy. So thanks a lot for inviting me. And I want now to talk about subject Picard theorem, basically. And the point is the question, how much values can a function avoid? So if we discuss over the reals, then of course functions can avoid a lot, as obviously the sinus function just assumes only values between -1 and 1, and so it avoids almost every value. And the interesting thing is that under the complex numbers, the situation changes. So one has a Picard theorem, and it tells you that if you have a holomorphic function from C to C, which is not constant, of course, then you can avoid at most one point. Of course, you can avoid one point by taking the exponential function, but you cannot avoid more than one point with a non-constant holomorphic function. So the situation improves a lot from the reals to the complex, and one can raise the question, what happens if you go further? Of course, the complex numbers are algebraically closed, so you cannot find another algebraic field extension, except if you are willing to drop commutativity. So the question I want to discuss is what happens with the Picard theorem if you study the quaternion numbers. So instead of the complex numbers, I go now to the quaternions. And first, I want to briefly recall the key structures of the quaternions. So the quaternions, this is real four-dimensional algebra, which is has all properties of a field except commutativity. So in particular, you have also a multiplicative inverse. You can divide, but you if you divide or multiply, then you must pay attention to the order of the terms. And it has a number of different descriptions. So maybe one easy description is that you say it is a real vector space of dimension 4. And then you have a rule, and the rules are simply that A, J, K are all imaginary units. And then you also have that I, J, K combined yields -1. And actually, then one can deduce all the other rules. So I, J, K is then K, and J, I is minus A, J, and JK is I, and KJ is minus JK, and so on. And this is one way to understand the Quaternion numbers. For many calculations, this is maybe the easiest way. But you could also put together two real components to obtain one complex component. And so you could think of the Quaternions as Z plus WJ. And J should have the property that, so Z and W should be complex numbers, and J has the property that J squared is -1, and J does not commute with the complex numbers. Instead, if you want to commute J with the complex number, you have to conjugate the complex number. So the non-commutativity is hidden at this point. And but there's also a geometric description, and this is sometimes also maybe the most useful. And this description is obtained by taking R plus R3. And now you take standard geometric constructions of R3 to define the multiplication. Namely, here you have some element SV, and you want to multiply with some element TU. So V and U are vectors in R3, and S and T are real numbers. And then you have ST plus the scalar product of V and U. And here you get S times U plus T times V plus then the non-commutative exterior vector product of two vectors. And here it is maybe most evident that in the algebra of the Quaternion numbers, you already have some reflection of the geometric structure, in particular of the scalar product. It really is somewhat built in the algebra of Quaternions. Okay, so one way or the other, you can describe that the Quaternions are skew field. They are also, in fact, just an example of a Clifford algebra. Special case, maybe you could say it's the most easiest example of a Clifford algebra. But now, how do we want to define functions here? And you could now think about analytic functions, which are given by a power series. And so you could just write a function in the form as a power series. And you can simply define this as the set of all, or the space of all Quaternionic entire functions. Here some comments are necessary. First of all, at this point now it becomes very strong, has strong consequences that the Quaternions are no longer commutative. Because the Quaternions are no longer commutative, if you multiply in the obvious way two such functions, they are no longer in an obvious way such a function, because simply AK, QK times BL QL, this will not be the same as AK BL QK QL. So actually, first, this is just a function vector space and not really an algebra of the real numbers. But still, this is now a natural candidate for generalizing functions. And so, and in fact, maybe I should now at this point mention that this builds up then of this theory of the so-called slice regular functions, which, if you regard the functions on the whole of the Quaternion numbers, are the same, but they are defined in a different way. And the crucial idea here is that you consider embeddings from the complex numbers into the Quaternion numbers. So in fact, you have lots of embeddings of the Quaternion, of the complex numbers in the Quaternion numbers as a real subalgebra, because you have many imaginary units. Here I wrote 3 down, but you can also combine these 3 basic imaginary units to get more imaginary units. So in fact, if you look at all algebra homomorphisms from the complex numbers to the Quaternion numbers, then they are described as follows. You must take an element in the complex numbers, x plus yi, and then you map it into x plus y, say times h, and h is an element in, I call this S. This is a set of all Quaternions, which have the property that q squared is minus 1. And now, if you, is it still there? Yes, at the top it is still visible, is a description in the geometric way. If you look at the geometric way of describing things, then you see that in the geometric way, so if you discuss it inside of R plus R3, then this is just 0 times the 2 sphere. So it is, in fact, you have infinitely many imaginary units. Again, this is possible because we have no longer commutativity. So we can actually take any element here, and this is an imaginary unit. You just can look at this equation here. If S and T are 0 and V and W is the same vector of length 1, then here you get wait a minute. Maybe I missed the minus sign here. Sorry, in the definition. And so if you have the same vector, then here you get minus 1 of length 1. And here, if it's the same vector, this one is 0, and if S and T is 0, this is all 0. So you get just minus 1 as a result if you take a vector in the 3-dimensional part of length 1. And the idea about slice regular functions is that you restrict H to an embedded complex subalgebra and demand that the function there should be holomorphic. And that, in the end, this just produces the same thing as these analytic functions by power series. And I think Strupper and Gentili developed this theory first. And well, but now the question is, how can one get a good theory and good proof things following, say, the results on complex analysis? If you just want to copy directly proofs of complex analysis, then, well, sometimes it works, but in many cases it does not. And also in the case of Picard theorem, it turns out that the situation is a bit more complicated. So a tool which is very important is now the theory of so-called stem functions. So what is a stem function? If you have such a function which is given by a power series, where everything here is quaternionic, one thing you could consider is, you could think is that you are more familiar with complex numbers. You are it's much more known in complex analysis. So it would be nice to consider the same function, but where the variable is no longer quaternionic, but instead it should be just a complex number. So what happens if you throw in a complex number in the place where we have the variable? Of course, the problem is now there are many embeddings of the complex numbers into the quaternionic skew field, but there is absolutely no canonical embedding. So in order to make sense out of this product, AK times ZK, so only canonical way is actually that you now take a function which has a value in the tensor product. So we just take the complex variable here. This gives you a complex number. And we have the coefficients which are quaternionic. And in the end, you get a function which goes from the complex numbers into the tensor product. And this tensor product now is as a vector space, just a four-dimensional complex vector space. And as an algebra, it's a bit more complicated. In particular, now, after taking this tensor product, we lose the skew field property. So now we will encounter zero divisors. So this is something which will happen now, that we get zero divisors. Well, and but my theory, actually, I completely forgot to mention that at the very beginning, of course, I should say this is all of this, which is all of the stuff which is new, is joint work with Giorgi from Ferrara. And so basically this is somehow was a joint project where Giorgi brought in a lot of expertise concerning quaternionic and me more expertise concerning Nevanlinna theory and things like that. And well, our goal is, as I stated, to prove a Picard theorem. So we have now a method by which we associate to a given quaternionic function a so-called stem function. But this other function is, of course, it's holomorphic. So it's available to, it's possible to use complex analytic tools. But of course, the question is, what is the relationship between the original function and the new stem function if we consider the question of which values are possible to take? And so what is really very important here is the connection between these two functions. And based on the theory of slice regular functions, then actually there is a connection which was developed by Giuloni and Perotti, and which goes the following way. You take this function, this can be described the connection the following way. You have this stem function, which is holomorphic and goes from the complex numbers into this tensor product. And now you want to understand the function value of this quaternionic function, small f. How can you do this? The answer is, if you have an arbitrary element in the quaternionic numbers, you can always embed a complex subalgebra which contains this element. So you can write Q as some x plus y h, and h is an imaginary unit. So h squared is -1. And this element you can now associate with an associated element in the complex numbers, just by replacing h with this standard imaginary unit of the complex numbers. And then you apply this big F. which is an element in H tensor C. And now you get a quaternionic number by simply translating back. So f of x plus y. Here you just substitute h for I. So basically, you identify the relevant you identify the relevant subspace of the quaternionic numbers in which the point to be considered is lying. And then you use this identification of the complex numbers to first apply the stem function, and then you can substitute the complex imaginary unit by this quaternionic imaginary unit to get a quaternionic number. And in this way, one can go from one side, from big F to small f. And in fact, one can also go the other way around. And the other way around follows in the following way. If I am interested in f of x plus yi, I have to consider small f of x plus y h, where h is an arbitrary imaginary unit. And now I take an advantage of the property that the imaginary unit, the complex numbers, is not really unique. It's unique up to conjugation. You have two roots of -1 in the complex numbers. And so we have also to consider x minus y h. And both h and minus h are imaginary units and can be identified with I. And if we use the fact that here we have the freedom whether we take h or minus h as the imaginary unit, in this way, actually, one can then, from starting from small f, also calculate big F. So in fact, the function values of the quaternionic entire function and the associated stem functions are related. There's a connection between the function values. And because there's a connection between the function values, it is not so surprising that one has the following theorem. If I have such a function, so f is now an entire quaternionic function, and big F is the associated stem function, then I can say there exists a quaternionic number where the small f assumes the value 0 if and only if we have a property about the stem function. And the property about the stem function is that there must exist some complex number we cannot expect here that we have to, we don't need here that it is 0. What we do need here is that it is contained in a certain subset, in a certain quadric. And this quadric now of the points where are actually arises from the quaternionic numbers in the following way. The quaternionic numbers are, as a vector space, isomorphic to R4. And here we have the standard scalar product. I mentioned already that the standard scalar product is related to the algebra structure. And so it's perhaps not too surprising. What happens if you now consider the tensor product? If you take the tensor product, then you can take the scalar product and also apply the tensor product structure. And what you get is some C bilinear form. So this is, I really mean a C bilinear form. So I don't mean in Hermitian product. In a product, I mean a C bilinear form. And because it is a C bilinear form, unlike the case of the scalar product, this can now be 0. And Q is the set of those elements in the tensor product where this is really equal to 0. So this defines, this is just one defining equation, which is polynomial. And so it is actually a complex three-dimensional algebraic subalgebra, subvariety of this C4. And we have 0 as function value for our function here, if and only if the stem function assumes a value inside of this quadric. In fact, this quadric also has some algebraic, could also be defined in an algebraic way, because this is here's the set. This coincides with the set of 0 divisors inside of this algebra. So as I mentioned, this one here, you always have a multiplicative inverse. This is a skew field. But if you pass to the tensor product, you no longer have a skew field. You get some elements which are 0 divisors. And these are those elements where this bilinear form yields the value 0. And obviously, in the quaternions, there are no such elements, because the scalar product cannot be 0 if the vector is not 0. So now we can say, if we have a couple of points and they are all not contained in FH. So if we avoid more than a number of points, what does that mean? This means now that 0 is not contained in the image. So 0 is not contained in the set of those points where f of q minus ci is 0. And we now get a new function, the difference of fqi with ci. And we can again use the characterization with this bilinear form. And so actually, yeah, so this is, no. So this corresponds somewhat to the set of complex numbers, let's say with where we have that b of z minus ci, z minus ci is 0. So, and in this way, we can now approach a result in one direction. I just want now to announce our result here, which is that one cannot avoid 5 points in general position. So if C1, C5 in general position, in H, this implies that there does not exist any F non-constant which avoids all these points. It's not possible to avoid 5 points in general position. And the idea of the proof is now that by this definition here, we get a couple of quadrics, and we get now a stem function. So assume the assumption is there exists such a function f. And if there exists such a function f, the consequence will be that there is a stem function, and the stem function avoids the union of all these quadrics. And each of these quadrics is defined by one function, this modified bilinear form. So in fact, we can now next define here a map to C star power 5, where in fact each element here will be mapped onto this B V minus Ci W minus Ci. So we can translate the fact that we avoid 5 quadrics into the fact that if we compose it with these functions, we get a map to C star to the power 5. And as one can already guess from the fact that here something is 4-dimensional and here something is 5-dimensional, in fact, this obviously they will not be surjective, and in fact it will be contained in a certain subalgebra. So the point is, so the image of F is contained in a certain subvariety of C star to the power F, to the power 5. Now you can explicitly write down this subvariety, but this is not really the crucial point here to see the exact definition. So what I want to want to emphasize now is that now we are in a classical complex analytic setup. Namely, we have a complex holomorphic map from C into some reductive complex Lie group, C star to the power 5, where the image should be contained in some algebraic subvariety. And so I can use some classical result, in particular the results of Noguchi-Bloch-Okiai, which state that if you have such a holomorphic map, which goes into some reductive complex Lie group, then the image cannot be contained in an arbitrary subvariety. In fact, such subvariety must be itself an orbit of a subgroup. So actually, we only need a special case here. So this special case tells us the following. If you have any holomorphic map from C to, let's call it G, C to some C5 holomorphic map. And if we now consider the image, so we take the image and we take the Zariski closure. So we take the smallest algebraic subvariety which contains the image. Here I really mean the algebraic Zariski topology. The statement now is then W is the orbit of an algebraic subgroup. Of our group C star to the power 5. In fact, this result holds for powers of C star, but also more generally for compact complex tori and semi-abelian varieties. But C star to the power 5 is the only case which we need here. And the crucial point now is that this is, of course, a very strong condition. Basically, only powers of C star are algebraic subgroups. If the only powers of C star can be connected algebraic subgroups of C star to the power 5. And so we got a strong conditions on the possible subvarieties. And if one carefully uses this property, then actually one can prove that this situation cannot arise. So that is the idea for proving that you cannot have a quaternionic entire functions, which avoids 5 points in general position. Yes? Yes, I'm getting there. Okay, this is what we got in one direction. And indeed, the question is this optimal or, and is it optimal in the sense that maybe generically 4 or 3 points can also not avoid it? Or optimal could also question whether this genericity condition really it's really necessary. And so the important bound from the other side is given by an example. So what can really happen if you want to avoid as much points as possible? Well, it's maybe this first example is of course the exponential map, but it's not very interesting. The exponential function just avoids the zero. The exponential function you can define for arbitrary algebra, so also for the quaternions you can define it, but it avoids just 1 point. That's not interesting. The interesting example which we found is the following. The function is sine of q j plus sine of well, let's call it j plus cosine of q k, and where actually j and k are these standard imaginary units which I used in the beginning for defining stuff. This function, if you look, I notice here you can really precisely describe the image of this function, and the image, it turns out, is h, and you have to remove everything inside of the plane generated by 1 and I. So here's the first big surprise. You can avoid infinitely many points. So it is for the statement about not possible avoiding 5 generic points, it's really essential that you discuss about generic points. You can in fact avoid infinitely many points, and you can also in fact avoid 3 generic points. And the reason behind this is basically the following. You should first of all translate this into a stem function. So actually, what does that mean here, sine of q? This just means that you all know the power series for sine and cosine, and the power series for sine and cosine have only real coefficients, so we can just plug it in some quaternion numbers because the real numbers are canonically embedded in the quaternion numbers. And the stem function then is also more or less like this. We just have to map the complex number to the complex number z times j plus, no, I switched it now, plus cosine of z times k. And this is now the stem function. And the point is now that we have to calculate, if we have an arbitrary element inside of this plane, whether we can fulfill the condition with this quadric. So let us take a plus bi with a, b, and r. And then we have to calculate what happens if with fz minus a plus bi. Now it's a little bit unfortunate. The question is, there's always a problem which imaginary unit, not to confuse the imaginary units of the complex numbers with the imaginary unit of inside of the quaternionics. I will write the quaternionics with uppercase. Then we have this one. And here, in fact, I have a little bit relaxed the notations. These are elements in H, and I consider H and also the complex numbers to be embedded in the tensor product in the obvious way. So this one is actually this. This is in the tensor product already by definition, but this one is just a quaternionic number and is to be understood as a quaternionic number tensorized with the 1 of the complex numbers. But the crucial point is now that here we have the 1 and I, and here in the function big F we have j and k, and these are transversal vectors inside of the space of quaternions. And so basically we have J, K, this is the space is orthogonal to the space generated by 1 and I. And so this bilinear form just decomposes into bilinear form applied only to F and the bilinear form of this complex, of this quaternionic number. This is true because here in the function, this function has a special form that we have a quaternionic power series, and the quaternionic power series only contains coefficients which are multiple of J and K. And therefore, we get inside of the space generated by J and K. And then we can use this orthogonal decomposition to decompose this, and then we can just calculate. And here we get cosine z squared plus sine square z. And of course, this is just 1. And now, that's the point. Here we get 1. And on the other side, we have A and B, which are, in this case, real coefficients. So these are real coefficients. And because these are real coefficients, they are actually real numbers which are at least 1. And so altogether, this means this is at least 1. And in particular, it is not 0. Which means that we can really avoid all points in one real plane. And in particular, we can avoid infinitely many points. So this example just works for this plane. But then, of course, one can modify it. One can modify the function a little bit by using automorphisms of the Quaternion algebra and translations and so on, which simply means that we could also use just an arbitrary plane and completely avoid all the points there. So actually, we can then summarize this to the following statement. If we have a subset inside of H, and then we say A should be the affine, affine R subspace. So this should be the smallest affine subspace of R4 of this real vector space H, which contains S. So this is generated by S. So you could also call this the affine hull of S. And the statement is now the following, that it's a bit too, I'm too small. So let me continue here. So the statement is, if the real dimension of A is at most 2, then we can find the entire quaternionic function from H to H, which completely avoids the image, which completely avoids S. And if the dimension of the set is 4, then there is no such function. Which in particular implies, if you talk about generic points, that you can always avoid 3 points, and you cannot avoid 5 generic points. And unfortunately, so far, I mean, we are still trying, but unfortunately, so far, the case in between for dimension 3, we have not answered until now. Well, but at least here we see that we have really that there is some statement, but there is some statement which is, of course, a little bit different from the situation of the complex setup. Also, of course, if you really like, you could say somehow formulate the same thing for the S and say you take also define A in the same way, and then you say you can avoid S if and only if the real dimension of the set A is 0. So in some sense, if you think about Picard theorem, not about as a theorem about the cardinality, but about the dimension of the affine hull, you could just also squeeze the classical complex Picard theorem into such a way. Okay, then one can produce some variants of this result, which I mentioned. In fact, we have also a version about a big Picard variant and something for the octonians. But anyway, I have enough time maybe to talk a little bit more, but I think this is the most interesting and striking results. And we had already a lot of mathematics this day, so let me just stop here.
Thank you. Questions, comments?
Sine and cosine of Q, those are quaternion functions, right?
Yes.
Or a quaternion variable?
Yes, I mean, we just take
but,
the usual power series.
Yes, but then you said that sine Q times J plus cosine Q times K only contains J and K. And,
well, I mean,
and that will not be true if this is a quaternion number, right?
Yes, it is true, because basically how does this bilinear product works? This bilinear product works in the following way. You have Z1 tensor 1 plus Z2 tensor I plus Z3 tensor J plus Z4 tensor K. And then this is just the usual bilinear product here.
Yeah.
And
right.
so this is just, in fact, you just have to use power series for complex numbers, for complex entries. And there it is obviously true that sine square plus cosine square is still 1.
Yeah. Okay. Yeah. Good.
Yeah.
Other questions, comments?
Or maybe it just let me just adjust one more remark here. In fact, it is something, but in fact, it is something one should verify, but it's easily verified that the usual rules for convergence of power series, convergence radius, and so on, they are all still valid for quaternions. In particular, sine and cosine, they really define globally convergent power series. But okay.
Yeah, my question is that, so because you are talking about the quaternions and you tensor with C over R, you have a 4-dimensional complex space. So which is actually 2x2 matrix, right?
Yes.
Yeah. And then you mentioned you have for the other theorem, you have a certain quadratic Q.
Yeah.
So is this quadratic Q, how is this quadratic Q related to this kind of a 2x2 matrix? Is that, for example, the determinant of a 2x2 matrix?
Yes, it is related. It is evidently related because, in fact, it has an algebraic description as being the set of all 0 divisors. So you just have to take the matrices and look what are the 0 divisors in the 2x2 matrices, and indeed these are precisely those who have determinant 0.
2x2 matrix and the square is 0.
If you have a 2x2 matrix and the determinant is 0, then either the matrix is nilpotent or it is diagonalizable like this. And in both cases, it is the 0 divisor. So really, it is just determinant equals 0. in this matrix picture.
Okay, thank you.
Okay, somebody else?
Well, of course, the number of points for this approach, the number of points which we can exclude depends also on the dimension of this algebra. The point is simply we take a map from the algebra tensorized with complex numbers, and then we take something to C star to the L. And the whole idea is that L must be larger than, and otherwise we could not apply Noguchi law or GI. So in fact, of course, the number 5 is specific for the Quaternions.
Actually, I have one question. You mentioned at the beginning you brought into this project your knowledge about the Neval-Lin theorem, and then there was nothing like Neval-Lin in your talk. So,
well, that's a delicate point. I mean, though the first idea was simply to prove as much Neval-Lin theory for Quaternionic numbers as possible, but it turned out that anything in direction of second main theorem, logarithmic derivative lemma, and so on, there are really serious problems. And so we started to wonder whether there is maybe some real obstruction here. And indeed, I mean, the second main theorem, immediately you can immediately deduce Picard theorem for, of course, from second main theorem. So the fact that the Quaternion numbers, it is possible to avoid infinitely many points. This tells you that the second main theorem, if it is can be proved at all for Quaternion numbers, must have a more complicated and unexpected form.
Okay, thank you. Anything else? No, then let's thank Joerg again.